No. Okay, all right. So recording is working fine as well. Okay, good. Let's begin then. So this is the first topic that we've got: modulus function, absolute value function. These are the two names that we've got for this function. The modulus function, you can call this modulus and also absolute value. Now, what does this function do? Whatever this function is applied on, what it does is it makes that thing positive. So modulus of -2, that is 2. Modulus of -5 is 5. Modulus of 7, that is just 7. So if you input something negative, that becomes positive. If you input something positive, that remains positive. Now, you need to be able to solve equations involving the modulus function. For example, if you have modulus x equals 6, then that means x is either equal to +6 or -6, because both of them will give you the same result. Now, a lot of times, the equations that you have to solve are more complicated than this. For example, you might have something like this, for instance, 2x plus 9 modulus equals 7. How do you solve such equations? This is how you would solve equations like this. You would remove the modulus sign and replace that with plus minus. Put plus minus on any one of the two sides, it does not matter. For the equations that you have in your syllabus, you can just put plus minus in any one of the two sides, remove the modulus sign, put plus minus here, and then divide your equation into two parts, one with the plus sign, one with the minus sign. Solve those two equations, you get the values of x from that. That's how we solve equations involving the modulus sign. You could have something more complicated like this. In the previous example, we had a constant on the other side. You can have some variable on the other side as well, like this. Again, you've got modulus here. All you have to do is remove the modulus, put plus minus in place of that. That will split your equation into two parts, one with the positive sign, one with the negative sign. Solve those two equations separately, you'll get the values of x, which will be the solutions of that equation. Okay. Now, what if you have modulus on both sides? If you have modulus on both sides, in that case, you might think at first that you should put plus minus on both sides. That's the logical way of doing this. But when you try that, what happens is you get only two unique cases. When you have plus plus or minus minus, both of them are exactly the same. When you have plus on the left side, minus on the right, or minus on the left, plus on the right, they also are the same equations. So when you have modulus on both sides as well, in that case as well, it is sufficient to put plus minus on any one of the two sides. In this case as well, you do not have to put it on both sides. Even if you do that, you will just get repeated equations. You'll get another x equals minus 4.5, you get another x equals minus 1.25, but the unique answers are only going to be these two. So if you have modulus on one side or on both sides, it doesn't matter. All you have to do is just remove the modulus sign, put plus minus on any one of the two sides, split the equation into two parts, and then solve those two equations separately. Okay. Now, the problem with modulus function is when you solve it using any way. So this is one possible method, using the plus minus method. There's another method that some of you might have done as well, and that is that you square both sides. In both of these, there's a problem. Sometimes you can end up getting some extra answers, which are not actually solutions of that original equation. Now, there's a logic behind it. We're not going to go into that right now. But whenever you are solving equations involving the modulus function, you always have to check your answers at the end. Always have to verify the answers at the end. For example, if you have this equation, you solve it using the plus minus method as we discussed, you get two values of x from this, x equals -8 and x equals -2/3. Now, these are multiple answers. Whenever you get multiple answers, in case of a modulus equation, that will be pretty much every single time that you would get multiple answers, you always have to verify them and see if they actually satisfy that original equation or not. So in this case, if I input x equals -8 in that equation and then simplify that, what I end up getting is on the left side, I have -11 and then modulus. Modulus of -11 is +11. And that gives me 11 equal to -11. And that's clearly not correct. So that means -8 does not satisfy the equation. If you try -2/3, you can see that working here. In that case, you get 11/3 equals 11/3, and that does satisfy the equation. So you would say only x equals -2/3 is the solution of this equation. Okay, so you always have to verify answers whenever you're solving equations involving modulus function. That's important. Okay, then what about inequalities? That's mostly what you have to do in case of this, in this topic, that you have to solve modulus inequalities. If you have something like this, Remember the modulus function, when it makes something positive, essentially what that means is, for example, if you have modulus of -5, what's that? That is 5. If you have modulus of 5, that's also 5. Modulus can be understood like this as well, that it represents the distance of this number from the origin. For example, if I have 0 in the middle, that's the origin. One number is -5, the other number is +5. How far are these numbers from the origin? They are 5 units away from the origin. So we get 5 as the result from both of them. Both of them have a distance of 5 from the origin. Now, if you have something like this, modulus of x is greater than or equal to 5. Now, what does that mean? Distance from the origin should be greater than or equal to 5. Now, on this number line, where is that possible? You should either be to the left of -5 or to the right of +5. So if you have an inequality like this, you can write it like this, that it's x less than or equal to -5 or x greater than or equal to 5, either to the right of 5 or to the left of -5. The numerical value, the magnitude of these numbers, for example, any number that's to the left of -5, for example, -7, its modulus, its magnitude would be greater than 5. Any number that's to the right of 5 there as well, for example, if you have 9 there, its modulus would also be greater than 5. So these are the two regions that satisfy this inequality. To the left of -5 and to the right of 5, we say x is either less than or equal to -5 or greater than or equal to 5. Similarly, if you had less than 7, what would you say in that case? The distance from origin is less than 7. So it has to be between -7 and +7. And we write that as a single inequality here, that x is between -7 and +7. Now, this is very important. Sometimes we write our answers as two inequalities. Sometimes we write them as a single inequality. You have to look at which region is satisfying the inequality. For example, in the first case, you have two separate regions. One is on the left side, another is on the right side. These are two separate regions. When you have two separate regions, you write down your answer as two separate inequalities. When you have a single region, you write that as a single inequality, and it's written such that the smaller number is on the left side. This is the convention that you always need to follow. Smaller number on the left side, larger number on the right side. Okay, whenever you write as a single inequality, smaller number on the left side, larger number on the right side, and in the middle you've got x, and you have less than signs like this, right? Less than or less than equal to, depending on what the original inequality has. That's what the format would be whenever you write something as a single inequality. Okay, now these were fairly straightforward examples, just modulus x is greater than equal to 5 or less than 7. In general, how do we solve modulus inequalities? This is the process that we follow for this. Let's say we want to solve this particular modulus inequality. Modulus of x minus 2, that is greater than 2x plus 6. Now, how do you solve this? For solving any inequality, it includes the modulus inequality, and as we will see later, polynomial inequalities like cubic inequalities. What you would always do would be, you would always solve it as an equation first of all. So solve it as an equation. Treat this as an equation and find the two critical points, find the two values of x that you get from that. So solve it as an equation. We know how to do that. We put plus minus on any one of the two sides, find the values of x that we get from that. Now, once we've got these values of x, for solving inequalities, what we do is we draw a number line. We draw a number line and we mark those points on that number line. So one point is -8 and the other point is -4/3. What we do is we mark those points on the number line. -8 is the smaller number, so we write that on the left side here. -4/3 is the bigger number, we write that on the right side here. And then these 2 points divide your number line into 3 different regions. One to the left of -8, one between -8 and -4/3, and another on the right of -4/3, right? These are the 3 different regions that you're getting from this. Now, what you would do would be, you would take one number in each of these regions and see if that satisfies the inequality or not. So take one number to the left of -8. You can try any number, it does not matter. You can try -10, for instance. Any number in the middle, for example, -5, or any other number, it doesn't matter. And one number on the right side. Input these numbers in the original inequality. What was the inequality? The inequality was this. modulus of x minus 2 is greater than 2x plus 6. Input these numbers there and see which of them satisfy. When we input minus 10, that gives us 12 greater than minus 14. That is correct. So that means the region on the left side is correct. In the middle, we had minus 5. We input that in the inequality, and that also turns out to be correct. We're getting 7 greater than minus 4 from that. That's also correct. And on the right side, we tried 0, and that gave us 2 greater than 6, which is incorrect. So the region on the right side is incorrect. This shaded part that you can see on the diagram, this is the solution of this equation. How would you describe this, of this inequality? How would you describe this? It's everything to the left of minus 4 over 3, and that's our final answer. X is less than minus 4 over 3. So that's the process that we follow for solving modulus inequalities. We treat them as equations, solve that equation, draw a number line, take one number in each of the 3 regions that we've got, input them in the original inequality, and see which ones satisfy. The one that satisfies, that means that region is correct. And the ones that don't satisfy, that means that those regions are not correct. And based on that, you write down the solution of that inequality. And that's how you solve this. Now, in this case, you saw that modulus was only on one side of the inequality. Now, when you have modulus on one side of the inequality, it's necessary to check all 3 regions, because it could be any combination of the number line. For example, in this case, we got that the left side and the middle region, that is correct, and the right region is not correct. We could have any other combination as well. It could be that the left region is correct and the other 2 are incorrect, or maybe that the right and the middle is correct and this is incorrect, or that the regions on the sides are correct and this is incorrect. There are many different combinations like this that are possible. When you have modulus on one side, you have to check every single region. However, when you have modulus on both sides of an inequality, in an inequality, when you have modulus on both sides, in this case as well, if you want, you can check all regions, and that's perfectly okay. But to make it a bit more efficient and save some time, you can remember when you have modulus on both sides, it's only going to be one of these 2 cases. It can't be any other possibility. What are the 2 cases? Either the middle region will be correct and the regions on the sides would be incorrect, or the middle region will be incorrect and the regions on the sides, they will be correct. These are the only 2 possible cases that you get when you have modulus on both sides. So in this case, you can just check, for example, the middle region. If that turns out to be correct, that means it's the first case. If the middle region is wrong, then that means that's the second case, and you would not even have to check the other regions, and that would save time, okay? But that's your choice in this case as well. If you want, you can check all of them as well, but you can save time when you have modulus on both sides by just checking one of these regions, and you would know which of these 2 cases it is, all right? But when you have modulus on one side, you do have to check all 3 regions. These are some examples. You can have a look at them. This is an inequality that we had here. We treated this as an equation. First of all, we got 2 values of x from that, minus 1 over 2 and 5 over 4. That divided a number line into 3 different regions. We took one number in each region, input that in this inequality. The left region was incorrect, the middle was correct, the right was correct, and we wrote down our answer based on that, x greater than minus 1 over 2. Now, in this case, you have modulus on both sides. In this case, you can see we could do it more efficiently now. We solved this as an equation, found one value of x minus 5, another value 1 over 3, and we drew a number line like this. And now, since we had modulus on both sides, we knew that it could only be one of these 2 cases, right? Either the first case here or the second case here. So we could just check the middle region. In the middle, we have 0. You can just try 0. 0 turns out to be correct. If 0 is correct, that means necessarily that the side regions are incorrect because you have modulus on both sides here. And based on that, you write down the answer. That's x between minus 5 and 1 over 3, and that's your solution. Okay. Sometimes you end up getting inequalities like this in which you have some constant written like this, a, for instance. How do you deal with these problems? The same way, you treat them as an equation. Find the values of x in terms of a this time. So in this case, you get x equals 7a, x equals 1 over 3a when you solve this as an equation, first of all. Then you mark those points on the number line. One of those points is 1 over 3a, the other is 7a. And that again divides your number line into 3 different regions. Now, when you take values in each region, you have to take those values in terms of a. Okay, you can't just write numbers randomly. For example, in the middle, you can't just write 4, for instance, or just 2, for instance. It has to be in terms of a. So in the middle, I've taken 2a here. On the right side, I've taken 8a here. You can't just write numbers. It has to be in terms of a. For 0, yes, you could just take 0 on the left side because 0 times a is still 0. So in that case, it would not matter. For everything else, it does matter that you take that in terms of a. Okay, so you take each 1 point in each of these regions, and then you just check them on the number line and see which one satisfies. In this case, the middle region satisfied, and we said x is between 1 over 3a and 7 times a. Since we had modulus on both sides here, we could save some time by just checking the middle region and just ignore the other, because we know if the middle is correct in this case, because we have modulus on both sides, in this case, we could say this is the only possibility that we can have. With the middle correct, the right and the left, they should be incorrect. Okay, and that gives us the answer. X is between 1 over 3a and 7 times a. Now, sometimes it's a very similar example. Like before, we have something in terms of a, but in this case, what happens is from the first equation, we end up getting something like this. X gets cancelled. The equation on the left side, you see that x ends up getting cancelled. X gets cancelled, and we get a equal to 0 eventually. Now, a is a positive constant, so that's not possible. The question says it's positive, so we're not getting anything from this. So that means we only have this one possible value that we're getting from this when we solve this as an equation, and that is x equals to a. What do we do in this case? In this case, we only have 1 point on the number line. So we mark that point 2a on the number line. That's only one possible solution that we got there from that equation. And now this divides your number line into 2 regions, one on the left, one on the right. You take one number in each of these regions. You can take 0 on the left side, for instance, 0 or 0a, doesn't matter for 0. On the right side, you can take 4a. Try these regions. The left side is correct, the right side is not correct, and you say the solution is x less than 2a. Now, sometimes this is also possible that you only end up getting 1 critical point and not 2. Okay. Now, you will see in some cases that you would have to use logs here as well. Now, we will talk about logs later on today, but you end up getting equations or inequalities that combine both of them. For example, you could have something like this: 2 into modulus of 3 raised to power x minus 1, that equals 3 raised to power x. Now, how do you solve this equation? You would do it the normal way. You remove the modulus sign, put plus minus on any one of the 2 sides. Now, be careful. When you put plus minus, do not put plus minus like this, that you say 2 plus minus 3 raised to power x minus 1 equals 3 raised to power x. If you remove the modulus from here, don't just put plus minus like this here, because that would mean that 2 is being added or subtracted to this bracket. It's actually multiplying. If you wanted to put plus minus on the left side, the way to do that would be that you put that in the beginning like this. Okay. Or to save yourself from confusion, you can just put that in the right side like this, plus minus 3 raised to power x. And then that splits this equation into 2 parts. You solve each of those equations separately using substitution, or you could do it directly as well, and then logs. We will talk about that later. You solve it in terms of using logs. You get some solutions from that, and then you can verify them if they satisfy that equation or not after that. All right. So sometimes you may have to use logs here as well when x comes up in the power like this. In this example, have a look at this. In the first part, they ask you to solve this equation. You solve it like you normally solve modulus equations. You get 2 values of x from that. X equals this and x equals this. And then in the second part, they say, hence solve this equation. Now, how is the first part related to this? You see, the second equation is very similar to that. If you compare the two, in place of x, in this second equation, we have 4 raised to power y. Here as well, in case of x, we've got 4 raised to power y, because 4 raised to power y plus 1 is actually 4 raised to power y into 4. So in place of x, we still have 4 raised to power y, and this 4 is multiplying with that. So what's happened in the second equation is that x has been replaced with 4 raised to power y. Now, what that means is whatever values of x we got from the first equation, now in the second part, and for this equation, those will be the values for 4 raised to power y. So 4 raised to power y equals minus 2 over 3, or 4 raised to power y equals 4 over 5. And then we solve those two equations separately using logs. The first one does not give us any answer. The second one, that gives you some answer using logs, and that's your final solution that you get from this. Now, in this case, they split it into 2 parts like this. It's not necessary that they would do that. They could just ask you to solve this equation directly as well. How would you do that in that case? You would remove the modulus, put plus minus in any one of the 2 sides, and then solve each of those 2 equations separately using logs like we looked at in the other example. Okay, so sometimes you may have to use logs in this case as well. Then you have modulus graphs. Finally, you have to sketch modulus graphs as well. How do they look like? If you have y equals modulus of 2x minus 6, how do you draw the graph of this function? Now, the idea is, one way to think about this is that it's the line y equals 2x minus 6. The part of this line that is below the x-axis here, because of the modulus, what happens is that gets reflected. The negative part becomes positive, and that comes here instead, right? So this was y equals 2x minus 6 line, the purple one. But then the negative part, because of the modulus, it gets reflected and comes up like this. Okay, that's what happens in this case. However, to make these graphs quicker, you can just follow this process like this, what I'm going to explain now. First of all, remember there are only 2 possible shapes that you can have for modulus graphs in your syllabus. It will either be a V shape, like the one on the left side, or it will be an inverted V, like this, right? V or inverted V. This number that's multiplying outside, if that is positive, then you have a V shape. If that is negative, then you have an inverted V. It's going to be one of these 2 shapes, depending on the number that is outside, whether that's positive or negative. Now, one important point that you always have to show on this graph in the exam is the vertex. This point is called the vertex. We have to show this point in the exam every single time. Now, how do you find that vertex? For finding the vertex, whatever is inside the modulus, you put that equal to 0. So in this case, if you want to sketch the graph of minus 2x plus 8, inside the modulus, whatever you have, you put that equal to 0, and that gives you x equals 4. The corresponding value of y that you get from this is 0. So your vertex here is going to be at 4, 0. That's where the vertex is going to be. So you mark that vertex. That's the vertex. That's the first thing you do. And then all you have to do is take 1 point to the left of the vertex, take 1 point to the right of the vertex. In this case, we got 0, 8. That was 1 point. Another point on the right side, that was 8, 8. And then starting from the vertex, draw a line in this direction. Starting from the vertex, draw a line in this direction, and that gives you the graph. Now, they also sometimes require that you show the y-intercept. Okay, it's only a 1-mark question, unfortunately, in the exam, and in that case they require that you show both the vertex and the y-intercept of the graph. So one idea could also be that you find the vertex and then find the y-intercept. How do you find y-intercept? You put x equal to 0. So in this case, if you input x equal to 0, the value of y that you get is 8. So y-intercept is at 8. So what you could do could be, you could draw that line on the left side from the vertex to there. And then you draw a symmetrical line on the right side. The symmetry is important. They specifically mentioned in the marking scheme that the graph has to be symmetrical. Okay, whatever is the gradient of this side, it should be the same gradient for the other side, just the sign being changed, but the slope should be the same. Okay, it should be symmetrical like this. If you have this example, if you had to sketch the graph of this function, what would you do? You find the vertex first of all. How do you do that? Whatever is inside the modulus, you put that equal to 0. Put 3x plus 9 equal to 0. And that gives you x equals -3, corresponding y value is 0. That's your vertex. You can mark that point here. This is the vertex. And then you can find the y-intercept. What's the y-intercept? You put x equal to 0. X equals 0 gives you y equal to -18 in this case. That's one point that you can plot. And then you'll have another point at the same distance on the other side. And then you just draw the graph like this, one line here and the other line here, and that gives you the graph of the modulus function. So vertex and y-intercept, they have to be shown, and the graph should be symmetrical about the vertex. Okay. Sometimes they can ask you to draw a graph like this as well, where you have a constant like this. For example, a. How would you sketch this graph? X minus 2a modulus, whatever is inside, you put that equal to 0. That gives you x equals 2a. That's the vertex. So the vertex is at 2a and 0. That's the point that you've got on the x-axis. Then you find the y-intercept. How would you do that? You put x equal to 0. When you put x equal to 0, you get 2a. That's the y-intercept. You mark these points on the graph. From the vertex, draw one line here, and then draw a symmetrical line on the other side that looks like this. The graph is symmetrical about the center. So, and these graphs that I showed you, if you were to draw a vertical line here in the middle at the vertex, the graphs are symmetrical. Okay. So whatever is what you get on one side, it should be a similar shape that you get on the other side as well. Okay. And in the second part, I just want you to solve this inequality. You can have a look at the solution I've shown you another example like this before as well. And that's all that you need to know about the modulus function. Yes, for understanding the shape of the graph, it's the number that is multiplying outside that matters. If that number that's outside, that's positive, you get a V shape. If that number is negative, you get an inverted V. But when you take points, you will automatically get one of these shapes, right? So when you draw the vertex, for example, in this case, I plotted the vertex, then I plotted the y-intercept. Now I know from the vertex, I have one line on this side. So the other line is obviously going to be like this. So it automatically turns out to be the V shape, okay? Because in this case, the number outside was 1. There's nothing outside, you can say that's 1. So that's going to be a V-shaped graph. Okay, so that's all that you need to know about modulus. I hope that was helpful. If there's any question now, you can let me know. I'll unmute you guys as well. That's a pretty straightforward topic. Easy 4 marks generally. Easy 4 marks. That's all that you have to do. Okay. Okay, so this is the next topic that we've got, polynomials. Now, what are polynomials? First of all of these different types of functions that you've seen, linear functions, quadratic functions, cubic functions. So basically, powers of x being added or subtracted like this, right? It could be power 3, 4, 5, 6, and so on. The condition is there should be positive integer powers. When you have fractional powers or negative powers, they are not part of polynomials. In polynomials, the powers have to be positive integers, right? So linear functions, quadratic functions, cubic, quartic, all of these are examples of polynomials. We categorize them as polynomials. Now, first of all, you need to know how to divide one polynomial by another polynomial. Just like you used to have division of numbers, you need to be able to divide polynomials as well, one polynomial by another polynomial. Now, we have a relation between these 4 things that you need to be aware of. We will be using this later on in integration as well. When you divide something, for example, in earlier years you've done this. If you have an improper fraction like this and you want to convert it to a mixed fraction, how do you do that? You do division and then you write it as quotient remainder over the divisor. We can write that as quotient plus remainder over divisor as well. And that gives us a relation between dividend, divisor, quotient, and remainder. What are these terminologies? First of all, this number that is being divided by something else, that's called the dividend. This number that you're dividing by, that's the divisor. What you have left at the end, that's the remainder. And this number on top, that's the quotient, right? There's a relation that we've got between these four numbers or four expressions, and that's like this: dividend over divisor. It can be written as quotient plus remainder over divisor. You need to memorize this. We will need to use this later on as well. Quotient plus remainder over divisor. Now, first of all, you need to be able to do long division. How does long division work? For example, if you have 4x squared minus 12x plus 3, you want to divide it by x minus 2 and find the quotient and the remainder from this division. How does this process work? You would write the dividend here like this: 4x squared minus 12x plus 3. The divisor outside, that's x minus 2. And then you think of it like this: what can you multiply this number x by to get 4x squared? You have to multiply it by 4x. So you have 4x in the quotient here as the first term. Then you multiply 4x with this whole thing. 4x into x minus 2, what does that give you? 4x squared minus 8x. So you have 4x squared minus 8x here. And now what we have to do is we have to subtract this expression from the expression on top. An easy way of doing this that reduces careless errors as well is that you change the signs of the expression and then you add them, because adding is simpler than subtracting. What you do is you change the signs. So you make it negative. 8x had a negative sign, you make that positive, and then you say 4x squared minus 4x squared, they get cancelled. Minus 12x plus 8x, that's minus 4x, and then 3 comes down as it is, minus 4x plus 3. And then you just repeat this process. You think of it like this: what do you multiply x by to get minus 4x? You'll have to multiply it by minus 4. So you have minus 4 in the quotient here. You multiply minus 4 with this whole thing. That gives you minus 4x plus 8. In the next step, you change the signs again. You change the signs. This becomes plus, this becomes minus. Now minus 4x plus 4x, that gets cancelled. And you have this left, minus 5. Now what do you multiply x by to get minus 5? You can't do this anymore, because now you'll have to divide instead. The power of x here is bigger than the power of x here. This is actually x power 0. So we can't do this. We can't do this any further. We stop at this point, and this is going to be the remainder. Okay, so now this division gives us the quotient on top there. That's 4x minus 4, and this is the remainder, and that's your final result. That's how this division process works. This is another example in which the polynomial is cubic. You do it the same way. You think of, what do you multiply x by to get 4x cubed? You multiply it by 4x squared. That's the first term that you get. Then you multiply 4x squared with this whole thing. That gives you this. Then you change the signs. In the next step, again, you do the same thing. You think of, what do you multiply x by to get minus 14x squared? You get minus 14x. You multiply minus 14x with this whole thing, and you get this expression. You change the signs again, and this process keeps repeating until you get something that has a lesser degree than this expression here. That was x power 1. We are getting x power 0 here, so we stop there, and that's your remainder, and this is the quotient. That's how this division process works. Now, sometimes you end up getting something slightly more complicated when you have some terms missing in one of the dividend or the divisor. In this case, there's nothing missing. You can have a look at this example in your own time. You can have power 4 polynomials as well, which you might have to divide by quadratic polynomial. So the divisor could be some bigger power like this as well. It could be quadratic. The process remains the same. In this case, we stopped when we got this expression. So the remainder does not necessarily have to be a number. It could be an expression like this as well. You have to stop when the power of the remainder becomes smaller than the power of the divisor, because then you can't go any further. X squared will have to be divided by something to get this. You can't do that. You stop at that point and you say this is the remainder. Sometimes you have some terms missing. For example, in this dividend, you can see there's no x cubed term. In such cases, it makes things simpler if you write 0x cubed in place of that missing term, right? That will make sure that the terms that you get in your division, they are properly aligned. X cubed over x cubed x squared under x squared, and similarly x under x. Otherwise, if you don't do that, the terms do not end up getting aligned like that, and it becomes very confusing at times, and you end up doing careless errors. So whenever you have any term missing, either in the dividend or in the divisor, what you should do is add a zero coefficient for that term. In this case, x cube was missing. So we said, let's have a 0x cube here in the dividend. And that will make sure that the terms end up being aligned. The rest of the process remains the same. You can have a look at that. Sometimes you can have something missing in the divisor as well. For example, in this case, you've got x squared plus 2. The x term is missing. So you write 0x in place of that. In the dividend, the x squared term is missing. You can either leave some gap like this, or you can have a 0x squared in place of that. And that will make sure that the terms are aligned and you don't do any careless errors, right? That's how the long division process works. Now, that's one major thing that you need to know about in this topic, how to divide a polynomial by another polynomial. Then you've got remainder and factor theorems. Now, if you had a polynomial like this and you wanted to divide it by some divisor, and find the remainder from that. Now, one idea could be that you did this whole division process and you got the remainder from that. That turns out to be 8. However, when the divisor is linear, in this case, it's a linear divisor. Linear means the power of x, the maximum power of x is 1. In that case, we can use something that we call the remainder theorem to find the remainder quicker. Okay, if you only need the remainder and not the quotient, in that case, we can use the remainder theorem in case of linear divisors. Now, how does that work? In this case, the divisor was x minus 2. Okay. What we do is we equate that divisor to 0. X minus 2 equal to 0. Whatever that divisor is, equate that to 0. You get x equals 2 from that. If you input x equals 2 in that polynomial, the result that you get from that, that's the remainder that you have from this division. So you could actually skip that whole process and just do this, put x equals 2 in this. If you just want the remainder, you would get that directly. Now, there's a logic behind it, why it works. This is basically the explanation of that. If you're interested, you can look at one of the detailed videos for that. So it comes from here, dividend over divisor, that's quotient plus remainder over divisor. When we rearrange that, we can be left with remainder when we put the divisor equal to 0. That's where it actually comes from. But this is the takeaway from that. Whenever you have any polynomial, and it is divided by a linear divisor, the remainder is given by P of A in this case. If the divisor is x minus A, the remainder is P of A. What does that mean? If the divisor was x minus A, what we have to do is you have to put that equal to 0 and see what value of x you get from that. X equals A. You input that in the polynomial and that will give you the remainder. So these are some examples of that. For example, if you had x plus 5, you put that equal to 0. That gives the x equals minus 5. The remainder would be P of minus 5. That you input x equals minus 5 in the polynomial and that will give you the result. If the divisor was, for instance, 5x plus 20, you equate that to 0 first of all, x equals minus 4, you input that in the polynomial and that gives you the remainder. That's the idea of the remainder theorem. It works for linear divisors, only for linear divisors. You put the divisor equal to 0, the value of x that you get, you input that in the polynomial and that gives you the remainder from that division. This is an example, you can have a look at that. We had to find the remainder, just put a value of x inside the polynomial and that gave us the result. Now, what are factors? Let's take this example. When we divide 35 by 7, for instance, what do we get? We get 0 as the remainder and the number on top is 5, right? Now, whenever the remainder is equal to 0 from any division, what that means is the divisor is a factor of the dividend. So 7 is a factor of 35, but not just that. 7 multiplied by 5 is actually giving us 35. So that means the quotient that we've got, that is also a factor of this dividend. So whenever from any division, the remainder turns out to be 0, both the divisor and the quotient, they are going to be factors of that polynomial. So for example, of that dividend, whatever that dividend is, it works for numbers. It also works for polynomials. Whenever the remainder is 0, divisor is a factor of that dividend, and the quotient is also a factor of the dividend. Both the divisor and quotient would be factors. Okay, whenever the remainder is 0, you have a factor. If you had to figure out, for instance, whether x minus 2 is a factor of this polynomial, how would you do that? It's a linear divisor. One possibility, of course, could be that you could use the long division, find the remainder. If the remainder turns out to be 0, then that means that it's a factor. However, since it's a linear divisor, we can do it more efficiently using the remainder theorem. Put this equal to 0, x minus 2 equal to 0, and that gives you x equal to 2. You put x equal to 2 in this polynomial, the value that you get from that is going to be the solution. That's going to be the remainder. The remainder turns out to be 0. If the remainder is 0, that proves that x minus 2 is a factor, because whenever from a division the remainder is 0, that means the divisor is a factor. So in this case, x minus 2 therefore is a factor. Now, how is that useful? This is one very common type of question that keeps repeating in the exam. Let's say you've got this polynomial ax cubed plus bx squared plus x plus 3. That's the polynomial that we've got. The polynomial is p of x. It's given that 3x plus 1 is a factor of p of x. Now, what does factor mean? Factor means the remainder should be equal to 0, right? So that's one thing that we're given. And they've also given that when p of x is divided by x minus 2, in that case, the remainder turns out to be 21. So division by x minus 2 gives us a remainder of 21. So we've got two pieces of information given. When we divide by 3x plus 1, the remainder is 0. When we divide by x minus 2, the remainder is 21. Okay. Now, both of these divisors are linear. So what we can do is we can use remainder theorem to make two equations. What we do is whatever is the remainder that's given, whatever is the divisor that's given, we equate that to 0 first of all. We say 3x plus 1 equals 0. Okay, whatever is the divisor, you put that equal to 0. And that gives you a value for x. When you input this value of x in the polynomial, that is what is going to give you the remainder. So we input this value of x in the polynomial, and that's the remainder. Now, since we knew that the remainder is equal to 0, for that reason, we equate it to 0 here. Okay. Similarly, in the second case, the divisor is x minus 2. Now, for finding the value of x that you want to input in that polynomial, you always put this equal to 0. Okay. In this case, the remainder is 21. You don't put this equal to 21. The value of x that you have to find out for that you would input in the polynomial, that will come when you input that divisor equal to 0. So you say x equals 2 in this case. You input that in that polynomial, that gives you the remainder, which is this. And then you say this remainder was given to be 21. So you equate it to 21. That gives you another equation. You've got two equations. You solve these two equations, you simplify them, solve them simultaneously, and that gives you the values of A and B. That's a very common question, keeps getting repeated every other paper. That's how you would do it. Okay, so you can have a look at this working. Then the next thing that you need to know about is how to factorize a polynomial and how to solve equations involving polynomials. Let's say we've got a polynomial that looks like this. It's a quadratic polynomial. Now, for quadratic polynomials, we know how to factorize them using middle term breaking, right? Using middle term breaking, we know how to factorize them. So if it was a quadratic factor, we could factorize them like this. But what if it was a cubic polynomial, for example, like something like this? Now, for cubic polynomials, we do not know how to factorize them directly. Okay, so in order to factorize cubic polynomials, we would need to know one factor given first of all, right? We would need one factor given, or there should be some way to find one factor first of all, and then we can factorize this. So in this case, they gave us that x minus 2 is one factor of this polynomial. If x minus 2 is a factor, can we find the other factor of this polynomial? How do you find the other factor of the polynomial? You would divide this polynomial 2x cubed minus 14x plus 12 with x minus 2 divided by x minus 2. Do that whole long division process. At the end, the remainder would be 0 because it's a factor. The remainder should turn out to be 0. And you'll have some quotient here. that quotient is going to be the other factor. As we discussed earlier, whenever the remainder is 0, both the divisor and the quotient, they are going to be the factors of the polynomial. They're going to be factors of the polynomial. Okay. So what we get from this is x minus 2 was one factor, and we've got another factor that's 2x squared plus 4x minus 6. So we could write that polynomial, which was 2x cubed minus 14x plus 2 plus 12. We could write that polynomial as x minus 2 into 2x squared plus 4x minus 6 now, using those two factors. So that's the factorized form. Now, when you get a quadratic factor, you should always think of whether you can further factorize this in any way. Using middle term breaking, you have to think of whether you can factorize this any further. In this case, they will often give you a hint about this as well by using this word completely, factorize it completely. So that's a hint for you that the quadratic factor that you get from that, it would be possible to factorize that further. You should do that as well. Okay. Even if they don't mention completely, you should still do that if that's possible. So we get this factorized form. Now the quadratic factor can be further factorized using middle term breaking. So that's what we do. We factorize that further, and we get 3 linear factors from that, and that's the complete factorization of this. In this case, we could also take 2 common from this and write that outside as well like this. That's also possible. Although that's not necessary, both of these will be acceptable. This is also acceptable. This is also acceptable. That's complete factorization. So that's how we factorize polynomials. You'll have one factor given, you would divide by that and get the other factor and write that in factorized form like this. Then sometimes you have to solve equations, polynomial equations. So if you have a polynomial like this and they want you to solve an equation, 2x cubed minus 14x plus 12 equal to 0, how do you solve this equation? Again, you first need to factorize this. You are given one factor. So the process that we followed above, you'll have to do all of that to first factorize this. Divide by x minus 2, find the other factor, and you get 2 factors from that, x minus 2 into 2x squared plus 4x minus 6, right? We get 2 factors from that. And now this product is supposed to be equal to 0. Now, how do we solve this equation? We've got a product, 2 things are multiplying and the result is 0. That means either the first is equal to 0 or the second is equal to 0. We put each of them equal to 0 separately, and we get the values of x that we get from that. X equals to from the linear equation. This is a quadratic equation. You can solve it as a quadratic, factorization, quadratic formula, whatever you prefer, and you get the values of x from that. These are the solutions of that equation that we were looking for. So factorization or solving equations, you'll have 80-90% of the process exactly the same. When they say factorize, we leave it in a form like this. Okay, I'm sorry. When they say factorize, we'll leave it in a form like this. We don't find the values of x. This is the factorized form, right? This is called factorized form. We leave it like this. If they want us to find the solutions of an equation, in that case, we would then put that equal to 0 in case that is what they're saying. If the polynomial is equal to 0 there, we equate that to 0 and find the values of x from that. Solving means finding values of x. Factorizing means you just write that expression as a product like that. Okay, so that's how this works. Now, sometimes what happens is you are not given any factor, right? It's rare, but you will find this in a few questions in past papers in which they do not give you even one factor. Okay, they don't give you even one factor. For example, they might ask you to solve this equation: 6x cubed plus 3x squared minus 41x plus 12 equal to 0. Now, how do we solve this equation? We don't have any factor given, so it's just this. Solve this equation. Now, how would this be done? You would have to guess one factor yourself. You'll have to guess one factor yourself. How will that be done? This is only possible when at least one of the solutions is an integer. You would only be able to guess one solution in this case. When there's at least one solution that is an integer. For decimal solutions, we cannot guess them. We can only guess integers. Okay. And what integers? whatever is the constant term in that polynomial, we would try factors of that. What are the factors of 12? 1, 2, 3, 4, 6, 12, plus minus each of these factors. If this equation has any integer solutions, they have to be among the factors of the constant term. You can't have any other integer solution apart from these numbers. That's the rule. Whenever a polynomial has an integer solution, it's always one of the factors of the constant term in the polynomial, plus minus the factors, right? It could be positive, it could be negative. So what you do in this case is you try each of these factors one by one and see which one satisfies. For example, you could say 6 into, you try one first of all like this, 6 into 1 cube plus 13 into, so I'm not inputting the whole thing, I'm just giving the idea, 13 into 1 whole squared minus 41 into 1 plus 12. You input that in your calculator. In this case, this is cube, this is square. You input 1 inside the bracket once, then you input -1, 2, -2, 3, -1, -3, 4, -4, 6, -6, 12, -12. One of them is going to give you 0 as the result. In this case, when we do that on our calculator, we would eventually find out that -4, when we input x equal to -4, that is giving us 0 as the result. You can try that here. X equals -4. That's giving us 0. That means this is a solution of this equation, x equals -4. Okay. Now you would have to try 1, 2, 3, -1, -2, -3, and eventually you will get one solution that is like this. Okay. Now, once you have this, I'll tell you a more efficient way of doing that in a moment. But once you have found this solution, then what you say is, if x equals -4 is a solution, then that means x plus 4 is a factor, right? If x equals -4 is a solution, and x plus 4 is supposed to be a factor. So then you do that long division, find the other factor, and then you write down the factorized form, solve those two equations separately, and you get the values of x from that. Okay. So sometimes you have to guess one solution like this as well. Now, that's too many factors to check. In this case, that will take time. What you would do would be, you would go to the equation solving function on your calculator, polynomial, cubic. Just input that there, 6, 13, -41, and 12. You'll get solutions from this. One solution is -4, another is 3/2, another is 1/3. So we're getting one integer solution and two decimal solutions. We cannot guess decimal solutions. Don't input x equals 1/3 or 3/2 and claim that you have guessed that. That's not how it would work. The integer solution that you're getting, in this case -4, you would just show the working for that here. Okay. You know that one of the factors here should work, but instead of inputting them all in your calculator and then that will take a lot of time, just use this equation solving function on your calculator that gives you -4. Then you just show working for this. X equals, showing this working is important. You have to show this working. X equals -4, input that in the equation and show that you get 0 equal to 0. That satisfies the equation. So that means x equals -4 is a solution. So x plus 4 is a factor, and then so on. That would give you the result. Now, there's a question that, is it possible that none of the answers are integers? Yes, it is possible. In that case, you would not get this question in the exam, because then you cannot do that. You can only guess one solution if one of the solutions is an integer. If none of them is an integer, then they would always give you one factor themselves. Otherwise, you would not be able to solve it. Okay. So you would only have to do this when one factor is an integer. All right. When one solution is an integer. All right. So that's one thing that you also have to do sometimes. Then the next thing is cubic inequalities. So sometimes you'll have to solve cubic inequalities as well. Now, how does this work? So for example, they might ask you to solve this inequality, 2x cubed minus 3x squared minus 4 less than 0. Given that x minus 2 is a factor of this polynomial, Now, whenever you have to solve inequalities, just like we're solving here, okay, so let me actually just go back here for a moment. If the x squared term was missing, that would not make any difference. You would still have to guess the solution like this. However, something came to my mind based on that question, and that was sometimes you could just have this 6x cubed plus 13x squared minus 41x equal to 0. Now, in this case, there's no constant term. In this case, you don't have to guess. You can just take x common outside, and that leaves you with 6x squared plus 13x minus 41 equal to 0. And you've got two factors already. You can solve this as a quadratic, and this gives you x equal to 0. So when there's no constant, in that case, you can just solve that directly by factorizing. But when you do have a constant like this, then factorization is not possible directly unless you know one factor yourself. So you will either be given that factor or you'll have to guess it like this. Okay, let's move on. Now, cubic inequalities. So let's say you've got this inequality given that you want to solve, and you're given one factor, x minus 2, of this polynomial, 2x cubed minus 3x squared minus 4. That's a factor that we're given. Now, how do we solve this inequality? What we do is we first of all treat this as an equation. We treat this as an equation first of all, just like we used to do in modulus inequalities here as well. We treat them as equation. First of all, treat this as an equation, factorize this like we did previously, and find the value of x that you get from this. You're getting x equals 2 here, and the quadratic factor is not giving you any factor. X equals 2, that's the only factor that you're getting from this. So now the solution of the equation is this, x equals 2. Now you think of that inequality. How do you solve that inequality? Now, do we say x is less than 2, greater than 2? How do you figure that out? It's not always going to be the same sign that you have here. And in questions, they often ask you to justify your answer. So you need to make sure that you follow the process correctly. You solve it as an equation. First of all, find the values of x that you get from that. And then you could use a number line, just like you used to do it for modulus. Draw a number line. You got one solution, x equals 2. Mark that here. You've got one region to the left of that, another region to the right of that. Take one number in each of these two regions. You can take one number on the left side. You can take 0, for instance, one number on the right side, for example, 3. Check them in the inequality and see which one satisfies. The left one satisfies, the right one does not. So we get x is less than 2. That is one idea. Now, when you have more than one solution here, now in one solution, the number line method is fairly quick. It doesn't take time. You just have to check two numbers. But sometimes it is also possible that you end up getting solutions from this quadratic equation as well. You might get two solutions from here as well. And then you have 3 solutions in total. On the number line, you'll end up getting 4 different regions. So checking all of those regions, that's going to take time. Another way to do such problems is that you solve the equation fully, just like you've done here. You find the values of x. In this case, you're just getting x equals 2. And then think about the shape of the cubic graph. You need to remember the shapes of cubic graphs for iteration later on as well. You need to sketch graphs of cubic functions. You need to know their shapes. These are the 4 possible shapes that you can have for cubic functions that you see here. Roughly, these are the 4 possible shapes for a function that looks like this: ax cubed plus bx squared plus cx plus d. If you have a function that looks like this, it can have these 4 possible shapes. How do you know which one of these shapes you would get? If the coefficient of x cubed is positive, you get the shapes on the left side, any one of these. If the coefficient of x cubed is negative, you get one of these shapes. Okay, now we don't need to be able to differentiate which one of these two is it going to be. That does not matter. But it's going to be one of these 4 shapes, the left ones when x cubed coefficient is positive, and the right ones when the x cubed coefficient is negative. And then what we say is, let's draw that graph. So in this case, the cubic function has a positive coefficient of x cubed. We can draw a graph like this, an upward sloping graph like this shape. It only has one x-intercept. That is when x is equal to 2 here. That's the x-intercept. Now, the inequality that we want to solve is this less than 0, right? So we could say y, this thing is y, right? That is less than 0. Where is that? Below the x-axis, this yellow region that you see here, this is y. This is where y is less than 0. What are the corresponding values of x that you get from that? X is to the left of 2. Okay, so you write that as the answer. X is less than 2. That's your final solution from that using the graph. Now, in this case, there was only one x-intercept, so we had to draw x-axis like this, such that it only intersects at one point. Sometimes you can have multiple x-intercepts as well. Okay, there's actually a sign going on here. We'll have a 1-minute break and then we'll see. We'll have a look at this example in the meantime. Okay, now sometimes what can happen is that you can get multiple solutions of that cubic equation when you solve that. So for example, you might have 3 solutions. Okay, let's say you've got 3 solutions and it's an upward sloping curve like this, as in the coefficient of a is positive, so it's like this. Overall, it's going upwards from left to right, and it has 3 solutions. Let's say those 3 solutions are -6, -1. I'll show you an example like this. There is one example that I've seen in the recent papers. I'll show you that. And 9, let's say. Now, let's say the inequality is greater than 0. What that means is y is greater than 0. Now, where is y greater than 0? Where do you have values that are above the x-axis? These yellow regions that you see here, this region and this region. How would you describe them? What's the solution going to be? You would say x is between -6 and -1. That's one possible region. Or x is greater than 9. That's the other possible region, and that's your solution. Okay, so you can have multiple regions like this as well, that they could be your solution. I'll show you one example later on of this as well. This is the last major concept that you've got. Sometimes you have to prove that some polynomial is always positive or always negative or never positive or never negative, right? So these are 4 different cases that you could have. How would you approach problems like these? Let's take this example for that. So we have this polynomial x raised to the power 4 minus 2x cubed minus 2x squared plus a. It's denoted by f of x. It's given that it's divisible by. So when they say divisible by, that also means that this thing is a factor, right? That's another way of saying that this is a factor. We first of all need to find the value for a. Now, how can we do that? How can we find the value for a? Can we use the remainder theorem here? If we just keep it as it is, this factor. This is a quadratic factor. It's a quadratic factor. In quadratic factors, we do not use remainder theorem. So what's the alternative? We can use long division. We can use long division to figure out what the value of a should be. We divide this, we do that division process. At the end, the remainder turns out to be a minus 8 in this. And then we say, since it's a factor, that remainder should be equal to 0. And the value of a that we get from that is 8. So a equals 8 from this. All right. Now the first part is straightforward. Just remember that we'll have to use the long division process here. Remainder theorem cannot be used. But then it says, show that f of x is never negative. Now they're saying, show that this polynomial is never negative. Okay. Now, how do you do that? You're not going to say that this is greater than or equal to 0 and find the value of x from that. We are not looking for some values of x for which this is not negative. We have to prove in general that this is never negative. It's not given that it's not negative. They want us to prove that it's never negative. How do we do that? This is the polynomial that we've got. Now it's a quartic polynomial, power 4 polynomial. We don't really know much about these polynomials, power 4 functions. So what we want to do first is we want to break them down into smaller polynomials so that we can understand them better. So it's a quartic polynomial. We've already done the division process in the first part. We were given one factor. This was one factor, x squared minus 4x plus 4. And the other factor we got in the quotient there. So these are the two factors that we've got. So first of all, what we do is we write this polynomial in factorized form like this. X squared minus 4x plus 4 times x squared plus 2x plus 2. You write this in factorized form like this. And then these are polynomials that are quadratic. Now, for quadratic polynomials, we know how their graphs look like, how to find their minimum point, maximum point. Now, these are both quadratic expressions. What we can do is we can find the minimum values of these two expressions. How do we do that? These are quadratic expressions, right? Quadratic expressions, they're going to be U-shaped if the coefficient of x squared is positive. So the first one is a U shape here. The second is also a U shape here. If we find the minimum points of these, can we do that? We can do that using minus b over 2a or differentiation or completing square. Using whatever method, what you can do is you can find their minimum points. I've used minus b over 2a here. The x coordinate of the turning point for the first expression, that turns out to be 2. The y coordinate corresponding, as in you put x equal to 2 in this expression, the corresponding y value that you get from that turns out to be 0. So this point for the first function, the minimum point is 2, 0. Now the value of a function is basically its y value, right? So the minimum value that we're getting for the first function is 0. We do the same thing for the other function as well, and we see what the minimum value for the other function is. We use minus b over 2a to find the turning point for that as well. X equals minus 1, and then y turns out to be 1. So the turning point for this function is minus 1 and 1. Minimum value, therefore, is this. That's 1. So minimum value of the second expression, that is also 1. So now the first function, the first expression out of these two, that is always greater than or equal to 0, right? If the minimum value is 0, that means it's greater than or equal to 0. And the second expression, the minimum value for that is 1. So that's always greater than or equal to 1. So we could say that one expression is greater than or equal to 0. The other expression is greater than or equal to 1. If we were to multiply them, the result that we get from that is also going to be greater than or equal to 0. There's no way that it can be negative because both the numbers, none of these numbers is negative, right? If none of these numbers is negative, then their product is also not going to be negative. So the overall expression, therefore, is never negative. That's what you figure out from this. This is one way of doing this. The other way you could be using completing square method, that you have these two expressions, you still have to factorize them. These are the factorized forms. You complete the square for both of them. The first one, when you complete the square for that turns out to be a perfect square. That's x minus 2 whole squared. You complete the square for the other one, and that turns out to be this. And then we could say the first expression, that's a square. A square can never be negative. So this is always greater than or equal to 0. This is a square plus 1. So that means this expression always has to be greater than or equal to 1. And then again, the product of these two is going to be something positive. Now, this is one of the confusing parts of a bit tricky parts of this topic. I hope that makes sense. So first of all, what we do is we find the quadratic factors from this. Once we have the quadratic factors, we find their minimum values. And if the minimum values for both of them are 0 or positive, then that means that the product is also going to be 0 or positive. Okay, this is another method for division. Now, this is optional. If you know this already, this is a quick reminder about this. If you don't know this, then it's okay. There's no reason to worry about it. You can do everything using long division as well. This is a bit more efficient in some cases when the divisor is linear. Okay, I'll just quickly go through this. So you can also do this when the divisor is linear. If you have this polynomial 4x cubed minus 4x plus 5, you want to divide it by x minus 3. How would this process work? How would this synthetic division work? We make a structure like this. We draw a vertical line and then two horizontal lines like this. The coefficients of the polynomial, we write them in the first row. And whatever is the divisor, we equate that to 0. And that gives us a value of x, that's 3. We write that number in this place. So this is the value of x that we are getting when we put that equal to 0, put the divisor equal to 0. And these are the coefficients of the polynomial. Okay, and now the way this process works is you first of all bring 4 down as it is, the first value that comes down as it is. And then you multiply 3 by 4, that gives you 12. You write that here, add these two numbers, that gives you 12. And then you just repeat this process. You multiply 3 by 12 now, that gives you 36. You write that here. Add these two numbers, minus 6 plus 36, that gives you 30. 3 into 30, 90. You write that here. And then you add these two numbers, that gives you 95. And that's it. That's the division complete. Now, the last number that you have here, that's your remainder, this number. And these are the coefficients of the quotient. Starting here, this is the constant, this is x power 1, this is x power 2. So you have 4x squared plus 12x plus 30. That is what the quotient turns out to be here. Right, that's another division process that you could use here. Now, this is when the coefficient of x is 1 here in the divisor. If the coefficient of x is not 1, for example, if it's 2x plus 4, then it's the same process. You equate the divisor to 0. That gives you x equals minus 2. Once you have that, you say this is minus 2, and these coefficients of the polynomial are 4, and then x cube is missing. We have to write 0 in place of that, and then minus 6, 2, minus 5. We follow that complete process as we did for the last example. The last number is going to be the remainder, that is 31. But then for the quotient, there's one additional step. You write down the coefficients like this. This is the constant x squared, x cubed. But then you also have to divide by the coefficient of x in the divisor. You divide by 2 here, you divide by 2 here, and that gives you the quotient. In the previous example, the coefficient of x was 1. So in that case, we did not have to divide by anything. Even if we did, that would not change anything. But in this case, we divide by 2 to get our final quotient. This only works for linear divisors, Otherwise, you would just use long division. So those of you who know this, you can use it like this. Don't remember to divide by the coefficient of x at the end for the quotient. Okay, that's a common error that happens. You can do everything using long division as well. So if you've not done this, that's perfectly okay. There's no need to worry about that. Okay, now we've got this polynomial. Let's have a look at some examples now. We've got this polynomial where a is a constant. It's given that 2x minus 1 is a factor of p of x. What does factor mean? Factor means that the remainder is supposed to be 0. The remainder is supposed to be 0. It says find the value of a and hence factorize p of x. Now, how do you do that? Okay, so that's actually a very straightforward example. For finding A, you can just use remainder theorem. Equate the remainder to 0, and then that will give you the value for A. Once you have that, to factorize, you have to do division. Now, since it's a linear divisor, this is just an example that I've shown there to show how the synthetic division process would work on this. You can have a look at this if you're interested. Otherwise, just use long division. It's just an example of synthetic division. But let's have a look at this now. What if you have something like this? This polynomial is divided, is p of x, and is given that this is a factor of p of x. We have to find the value of a and hence factorize p of x. Now, this is a quadratic factor. When it's a quadratic factor, remainder theorem does not work. Synthetic division also does not work. In this case, we just do long division, right? So x power 4 plus 5x plus a. Now you see the x cubed term is missing, x squared term is missing. We write zeros for both of them here when we divide this. We do this whole long division process. At the end, the remainder turns out to be a plus 6. And we say this should equal 0. So the value of a that we get from that is equal to minus 6. Then it says, hence state the number of real roots of this equation, justifying our answer, number of real roots. How do we do that? We have found the factors of this polynomial. One factor was given. This is the other factor. So we can write this in factorized form. This is the factorized form of the polynomial. In fact, we have done that in the first part already. We have factorized it completely. Now, we just put that equal to 0 and see the number of solutions we get from that. Two linear factors, they give us two solutions here. But the quadratic factor, it turns out that it cannot be solved. When you try solving it, you end up getting a negative number inside the square root. So that's not giving you any solution. You have to show this working. The question says justify your answer. That means working is important. You have to clearly show either that the discriminant is negative, that is why we're not getting any solutions from that, or input values in the quadratic formula. When you do that inside the square root, you would end up getting something negative and you would say that it's not solvable. So the only two solutions that we're getting from this are the two real solutions, which are -2 and 1, and that's our final answer. So we write two solutions. Now, sometimes you will see a couple of questions and recent past papers as well. They have differentiation involved with polynomials somewhere. This is an example of that. We have this polynomial f of x, and it is of this form: x minus 2 whole squared into g of x. And g of x is another polynomial. Show that x minus 2 is a factor of f prime of x. Now, what's f prime of x? That's the derivative of f of x. Now, how do you find the derivative of this? Now, we will discuss this later on when we do differentiation, but using product rule of differentiation, what you can do is you can differentiate it, right? X minus 2 whole squared into g of x, you can say that's u into v. The derivative is going to be uv dash plus vu dash. So x minus 2 whole squared as it is into derivative of g, that's g prime of x, plus g of x as it is into derivative of x minus 2 whole squared, that turns out to be this. Now, we have to show that x minus 2 is a factor, show that x minus 2 is a factor of the derivative as well. Now, what's the derivative that turns out to be? From this is the derivative. This is f dash of x that we're getting. Now, we have to show that x minus 2 is a factor of this. One way to do this could be that we put x equals 2 in this polynomial, and that will make everything 0. So the remainder is 0, and that means that it is a factor. Alternatively, we could take x minus 2 common here. Both of these terms have x minus 2. We could take that common outside and then say, since it's common outside, it's multiplying with the whole thing, this is a factor of this polynomial, x minus 2 is a factor. Then in the second part, it says, this polynomial has a factor x minus 2 whole squared. So now they've given us a specific example. Earlier, they just said there's f of x, that's a general polynomial that looks like this. Now look at this polynomial, it's x minus 2 whole squared into g of x. X minus 2 whole squared is multiplying with the whole thing. So for this polynomial, you see x minus 2 whole squared is a factor, right? It's taken common outside. It's taken common outside. Okay, you're right about that. You're actually right about that. There's something wrong inside here. So inside the bracket, it should have been x minus 2 into g dash of x plus 2 into x minus 2. That's what you have inside the bracket. Okay, I don't know if that was a simplified form, or that was just probably just wrong. This is what you have inside, x minus 2 into that whole thing. So x minus 2 is a factor. Now, if we look at the form that we had given for f of x in the first part, that was x minus 2 whole squared into g of x. X minus 2 whole squared is common from that whole expression, right? X minus 2 whole squared is common with that whole expression. Okay, I'm sorry. What am I doing? I took x minus 2 common outside, and that left me with 2g of x here. Yeah. Okay, let's actually go back to that now. So again, let me repeat. So what were we doing? In the second part, we were given this polynomial, and they said that this polynomial has a factor x minus 2 whole squared. In the first part, we had this polynomial given, f of x, and it was of this form, x minus 2 whole squared into g of x. Now, that basically tells you that x minus 2 whole squared is a factor of this polynomial f of x, okay? So for any polynomial that has x minus 2 whole squared as a factor, we have proved that its derivative, f dash of x, would have this factor. Now in the second part, they're saying there is a polynomial, there's a specific polynomial now, and this polynomial has x minus 2 as a factor, x minus 2 whole squared as a factor. That's what they've given. They're saying use the factor theorem and the result of part 1 to find the values of a and b. Now, how do you do that? Now, this is the polynomial x raised to power 5 plus ax power 4 plus 3x cubed plus bx squared plus a. We are given one factor for this, x minus 2 whole squared. We could consider this as x minus 2 into x minus 2, right? So there's one linear factor that we've got from this, that's x minus 2. We can use remainder theorem on this, put x equals 2 in that. Remainder equals p of 2. Since it's a factor, it has to be equal to 0 here. We put the remainder equal to 0, and that gives us this equation. But then, how do we use the first part? In the first part, we proved that if any polynomial has x minus 2 whole squared as a factor, then its derivative should have x minus 2 as a factor. So what we do is, we say, let's find the derivative of this. Let's find the derivative of this polynomial. That's what the derivative turns out to be of that polynomial. Now, using the result of the first part, we know that this derivative is going to have x minus 2 as a factor as well. So we use remainder theorem on this as well, and we say, let's put x equals 2 in this derivative. And the remainder from this should also be equal to 0. So we get another equation from this. We got one equation from the original polynomial, one equation from the derivative. We can solve them simultaneously to find the values of a and b like this. Okay, solve them simultaneously and you will get the values of a and b. You can solve it further and you will get that result. Okay, let's move on. Just a couple of examples, then we have a break. Okay, let's have a look at this. Now, this is something a bit more complicated. Sometimes you end up getting a long division that is quite complicated. For example, in this case, we have 2x raised to power 4 plus ax cubed plus bx minus 1, where a and b are constants. It's denoted by p of x. When it is divided by x squared minus x plus 1, they are saying that the remainder is 3x plus 2. Find the values of a and b. Now, when you have a constant in the very beginning like this, ax cubed, and you have bx is okay, but a is appearing in the very beginning. When you do long division in this case, the long division becomes quite complicated. So let's see how this would work. You've got 2x raised to power 4 plus ax cubed plus 0x squared plus bx minus 1. That's the polynomial that you have. You want to divide it by x squared minus x plus 1. Now, you start that process. In the first step, nothing complicated happens. You get 2x squared minus 2x cubed plus 2x squared. But now, when you subtract this from the first term, when you do this subtraction, ax cubed minus 2x plus 2x cubed, it's very important that you write it in an appropriate form. You would not write it as ax cubed plus 2x cubed separately. you should write it together like this, a plus 2. That whole thing is the coefficient of x cube. We say it's a plus 2 whole times x cube like this. Okay. We write it like this because then in the next step, that means what do we have to multiply x squared by to get a plus 2 whole x cube? We would have to multiply this by a plus 2 times x, this whole thing. That's what we have in the quotient above. A plus 2 whole times x. We multiply this whole thing with this here, and that gives us this result, right? You can have a look at this working slowly later on as well. And now you change the signs, this whole thing gets cancelled. And now in the next step, you have minus 2x squared here, plus a plus 2 whole times x squared here. You simplify the coefficient, it becomes minus 2 plus a plus 2, and that gives you a. You get ax squared here. So what do you multiply x squared by to get ax squared now? You multiply it by a, that's what you have in the quotient, a into that whole thing, that gives you this. Again, you subtract them and see what that gives you. In the last case here, in the previous step here, notice what I've done here. We had bx minus a plus 2, bx minus a plus 2. We had bx there and minus into a plus 2. When we write this in the next step, this is how we should write it. B minus a minus 2 whole times x. X should be common outside. Okay, x should be common outside. This is very important. Do not write it separately. That will make you do errors. Write it in brackets like this. Take x common, write the whole coefficient together. So eventually what happens at the end is that you end up getting this remainder. You cannot go any further than this. And now they gave us in the question that the remainder should be 3x plus 2. We are getting b minus 2 into x minus a minus a. We compare the two. We say that means b minus a should equal 3. And minus a minus 1 minus a should equal 2. And that gives us the values of a and b from this. A equals minus 3 and b equals 5. That's the value that these are the values of a and b that we end up getting. Sometimes they will say that the remainder is 0, for instance. What about that? If they had said in this case that the remainder is 0 and we were getting b minus 2 into x minus 1 minus a, if the remainder was equal to 0, we would think of that as 0x plus 0. So we would equate the x terms separately to 0, b minus 2 equals 0, and the constant term separately to 0, minus 1 minus a equal to 0. That gives us b equal to 2 and a equal to minus 1. So if the remainder was 0, 0 remainder means it's 0x plus a in this case. If we're getting something in terms of x, they've just said 0. That's what we think of this. We equate each term to 0 individually. In this case, the remainder was 3x plus 2. In this case, the remainder was 3x plus 2. Sorry. So we equated b minus 2 to 3 and minus a to 2, and that gave us the values of a and b like this. Okay, so this is quite complicated. As in the working here, it very high chances of doing careless errors here. So you have to be careful in this working. Okay, let's move on. Okay, let's have a look at this. We have this polynomial 6x cubed plus ax squared plus bx plus 9 is denoted by p of x, where a and b are constants. It's given that x minus 3 is a factor. That means remainder is 0. And when the first derivative p dash of x is divided by x minus 3, the remainder is 72. So you use the remainder theorem twice, one on the original polynomial, that's the original polynomial, and this is the derivative. They're saying for the original polynomial, x minus 3 is a factor. So we put x equal to 3 in that and equate that remainder to 0 here. That gives us one equation. The second thing is for the derivative. They're saying the derivative, so that's this. When this is divided by x minus 3, the remainder is 72. Again, we put x minus 3 equal to 0. That gives us x equal to 3. We input x equal to 3 in this polynomial. and we equate that result to 72, and that gives us another equation. Solve them simultaneously, and you get the values of a and b from that. Now, in the next part, they are saying when a and b have these values, factorize p of x. We factorize that using the factor that we were given. X minus 3 was one factor. We have factorized it like this. But then in the third part, they say, hence solve this inequality now. P of x less than 0, this is the inequality that they want us to solve next. How do you solve inequalities? We treat them as equations first of all. Solve this equation. We put this equal to 0 and solve this equation. What values of x do we get from that? X equals 3, x equals 1 over 3, x equals minus 3 over 2. We're getting 3 possible solutions of this equation. Now we could either think of the number line, but that will take a bit long, or about the cubic curve. The polynomial that we've got here, it has the positive coefficient of x cubed. So the shape of the graph would look like this. It has 3 x-intercepts. You mark them there: minus 3 over 2, 1 over 3, and 3. Inequality sign is less than 0. So we are looking at the region on the graph where y is less than 0. That means below the x-axis. You can see the highlighted parts here. It could either be this part or this part. How would you write down the values of x corresponding to this? To the left of minus 3 over 2, or between 1 over 3 and plus 3. That's what your solution would be in this case. This is an actual past paper question. I think it's just March 2025. It's the first time that they've given an inequality in which you get 3 x-intercepts like this. So you can do it using the graph like this. X is less than minus 3 over 2, or x is between 1 over 3 and 3. That's the solution that we get from this. Okay, so that's all that you need to know about polynomials. I hope that was helpful. If there's any quick question, let me know. Okay, everyone, let's begin with our next topic now. So next we've got partial fractions. That's another relatively straightforward topic. Now, what are partial fractions? First of all of you know how to take LCM of two fractions, right? So if you have two fractions like this, if you were to take LCM of them, you would end up getting this after simplification. If you want to do the opposite of that and go from this one single fraction to those two fractions, this process in which you go back to those separate fractions from a single fraction, this process is known as partial fractions. Okay, it's called finding partial fractions. Now, how do you do that? For this, first of all, you need to know the concept of an identity. So if you have an equation like this, for example, 2x plus 4 equals 10, you get a solution from this, that's x equals 3. Now, for any equation, you only have some specific values of x that satisfy that equation. For example, in this case, for this equation, only x equals 3 satisfy this equation. If you have a quadratic equation, you can have 2 solutions for that. If you have a cubic equation, you can have 3 solutions for that, and so on. Identity, on the other hand, is different. For example, if you have something like this, 2x plus 6, that's identical to 2 and 2x plus 3. This is something that's true for all values of x. No matter what value of x you input in this, the left-hand side and the right-hand side, they will always be equal to each other. This is called an identity, because the left-hand side and the right-hand side, they're just two different ways of writing the same thing. Okay, so whatever you input on both sides will always be equal to each other. Equation is different. That's only true for some specific values of x. So what we want to do here is we want to write this single fraction as two separate fractions. But these are two different ways of writing the same thing. So they will be identical to each other. When we take LCM, what we have is, in the denominator, we've got fraction here, another fraction here. When we take LCM of them, we get a single fraction in which we have a product like this, x plus 4 into 2x minus 6, right? When we want to go back, if we have 8x minus 38 over x plus 4 into 2x minus 6, what happens is we say we will get two fractions like this, such that one of them will have the denominator x plus 4 and the other will have denominator 2x minus 6, right? So finding the denominators is very straightforward. We just split them like this in the two fractions, among the two fractions. The first would have x plus 4 as the denominator, second would have 2x minus 6 as the denominator. Numerator, however, is something that we don't know what it is going to be. So what we do is we follow a process like this. We say, okay, this is one fraction. We want to write it as two separate fractions. We know the first fraction is going to have this denominator, the second fraction is going to have this denominator. What about the numerators? That's what you have to find out. Now, this is the form that we use for this. We write some constant in the numerator. This constant is a, this is b. And the problem is, how do you find the values of a and b from this? Now, the process that we follow for this is, first of all, we multiply the denominator on the left side and the right side. We multiply that on the right side. Now, what happens to the first fraction when it gets multiplied by that denominator? X plus 4 and x plus 4, they get cancelled, and we're just left with 2x minus 6 from there. When the second fraction gets multiplied with this denominator, 2x minus 6 and 2x minus 6, they get cancelled, and we're left with x plus 4, that's multiplying with b here. So we first of all remove the fraction by multiplying this thing on the right side. Then the idea is we want to find the values of a and b. For that, we input some specific values of x that would eliminate one of these unknowns so that we can find the value of the other unknowns. Since these are identical to each other, the left hand side and the right hand side, we know that they are going to be true. This identity is going to be true for any value of x. So we can input any random value of x and both sides would satisfy. So we input a value of x such that if one of these variables gets eliminated, for example, what one value of x that we can do is that we can input is x equals 3, because when we put that, the first bracket, this becomes 0. So the idea is we equate each bracket that we have to 0, whatever we have inside one bracket to 0, and see what value of x we get from that. So 2x minus 6 equals 0, that gives us x equals 3. If we were to input x equals 3 in this, what happens is this whole thing is going to get eliminated. Now I've done that here. So I've done that second. X equals 3. I've input x equals 3 there. On the left side, we have to input that value of x in both sides. When we input that here, we get 8 into 3 minus 38. On the right side, we get a into 0. A into 0, that's a 0. And that just leaves us with b into 3 plus 4. And from that, we can find the value of b, which turns out to be minus 2. Similarly, we try to input another value of x. How can we make this bracket 0? X plus 4 equal to 0. That gives us x equals minus 4. So if we were to input x equals minus 4, what happens is b gets eliminated now because b into 0, that will become 0. And we just have a left. We input the value of x as minus 4 in the rest of the terms and solve that equation to find the value of a. We get the values of a and b, and that gives us the partial fractions that we were looking for, 5 over x plus 4 minus 2 over 2x minus 6. And that's our final partial fractions that we get from this. Okay, that's the process that we follow for this. Now, there are two types of fractions that we would have. One is proper fraction and the other is improper fractions. For now, we're just talking about proper fractions. We'll talk about improper later, and I'll tell you the difference between them as well. Or for now, I'll just tell you this much, that the degree of the numerator, when it's less than the degree of the denominator, that's a proper fraction. In this case, numerator is x squared, denominator is x into x into x, that's x cubed. So this is a proper fraction. So for now, we're just talking about proper fractions. How would you do this? You would say, this is the fraction for which you want to find partial fractions. You break it into three fractions like this: a over x minus 1 plus b over x minus 2 plus c over x plus 1. You multiply the denominator on the left side and the right side, and that gives you this. And then what you do is, you input some specific values of x. For example, how can you make this bracket 0? You put x equals 2. You input x equals 2. What happens is, whichever term has x minus 2, that will become 0. So these two terms get eliminated, and we're just left with b into 2 minus 1 into 2 plus 1, and that gives us the value of b. When we input 2 on the left side as well, we get an equation. We get b equal to 4 from that. Then we see what other bracket we can make 0. We can make this equal to 0 by inputting x equals minus 1. So we can input minus 1, and that eliminates these two terms. We're just left with c, and we can find the value of c from that. That's what we get from this. And similarly, we can say we have got another bracket here that we can make 0, x equals 1, input x equals 1 there. That gives you the third unknown as well, and you got your partial fractions. Okay. The three different forms that you would have for partial fractions, the example that I showed you earlier, they were in which the denominator were all linear factors, right? They were all linear factors, this, and this. When you have a fraction like this, in which the denominator is two or three different linear factors, or whatever number of different linear factors, the partial fractions form that we get for that is this. In the numerator, you have constants. In the denominator, you've got those separate denominators, those factors one by one. The first will have 2x minus 1, the third has x plus 3, the second has x plus 3, and the third has x minus 4. We get these three fractions, and now we just follow that process that we talked about, multiply this denominator on the right side, and then simplify everything, put some values of x to solve that further. When we have repeated linear factors in the denominator, what happens in this case is, for any non-repeated linear factor that's appearing, for that we will just do a over x plus 5. But this is x minus 3 whole squared. We call this a repeated linear factor. We can think of it like this. This is x minus 3 into x minus 3. So x minus 3 is repeating here. When we have something like this, in this case, the partial fractions form that looks like this. We have one fraction in which x minus 3 is the denominator, and another fraction in which x minus 3 whole squared is the denominator. So we consider one power x minus 3 of x minus 3 in one denominator and power 2 in the other denominator, and that is going to come in two fractions like this. Okay, now there's a logic behind it. I'm not going to go into that right now. You can again watch the detailed videos for understanding that if you're interested. This is all that you need to know for exam. You need to remember these conditions, these forms. This is the form that you would get. Now, you won't see any example in the past papers until now, but in the recent past papers, they are trying new things. So what if you end up having a cube there? What would happen in that case? In that case, you would say this is a over 2x minus 1 plus b over x minus 5, b over x plus 5. You consider power 1 first, and you consider power 2, and then power 3 like this, right? So it's the same pattern that appears here as well. In earlier case, the power was 2, so we consider x minus 3 power 1 and x minus 3 power 2. In this case, we consider x plus 5, x plus 5 whole squared, x plus 5 whole cubed. All right. This is what happens when you have repeated linear factors. This is still a linear factor inside, but it's repeating. When you have a quadratic factor means you have x squared like this, not whole square, but you have a square on x. That's a quadratic factor. In case of quadratic factors, in the numerator, we consider two terms, one x term and one constant term. So in this case, we could say it's a over x minus 2 plus bx plus c over 3x squared plus 1. That's the form that we've got for this. The process will remain the same. We'll multiply this denominator on the right side. Then look at the brackets, what you can make 0, and input those values of x. We'll have a look at these examples later. But that's the idea. These are three different forms that you can have: non-repeated linear, repeated linear, quadratic factor. If all of them were to come combined, again, it hasn't happened until now, but the idea would be the same. The non-repeated linear factor, that's a over 3x plus 6. The repeated linear factor, for that, you'll have two fractions, one with x minus 2 in the denominator, another with x minus 2 whole squared in the denominator. And then you have a quadratic factor, that's bx plus e over x squared plus 4. Now, sometimes you will see later on, especially in integration, you might end up getting something like this: 3 over 2x minus 1 into x squared minus 4. Now, the first factor is linear. For that, we just have a over 2x minus 1. But consider this is, have a look at this. This is a quadratic factor, as in that's what it appears to be initially. However, this is something that can be factorized further. X squared minus 4, we could write that as x plus 2 into x minus 2, so that it becomes two different linear factors. So if you had to find partial fractions for this, we would have to break it down into parts like this, first of all, to make it x plus 2 into x minus 2. And then we say this is b over x plus 2 plus c over x minus 2. For this, you cannot do bx plus c, because you cannot do bx plus c over x squared minus 4, because the idea of partial fractions is we want to break the fraction down as much as possible. This fraction can be broken down further, so that is not acceptable. You'll have to factorize this and then find the partial fractions. Again, integration later on, you'll also see expressions like these. For example, if you had 3x plus 7 divided by x squared plus 7x plus 12, and they wanted you to find partial fractions for this. Now, in the denominator, there are no factors as such. However, you can actually factorize the denominator, first of all, to write it as x plus 3 into x plus 4. And then you write the partial fractions form as a over x plus 3 plus b over x plus 4. So sometimes it is possible that the denominator is not already factorized. You first have to factorize that and then find partial fractions of that after that. Okay. Now this is what happens in proper fractions. These are some examples of that. If you have a quadratic factor in the denominator like this, what would happen in that case? You'll say this is a over 1 plus x plus bx plus c over 1 plus 2x squared. For the quadratic factor, we have bx plus c in the numerator. Now, you multiply the denominator on the left side to the right side and see what that gives you. When you multiply the denominator on the right side, in this case, what you end up getting is a into 1 plus 2x squared here plus bx plus c whole times 1 plus x there, right? Now, you think of what brackets you can make 0 in this case. The first bracket, 1 plus 2x squared equal to 0, that does not give you any solution. So you're not getting any value of x from this. The other bracket, 1 plus x, can you make this 0? Yes, x equals minus 1. So that's what you can start with. You can say, let's input x equals minus 1 on both sides. That will eliminate this whole thing. And you can find the value of a from this. That turns out to be minus 1. Now we have run out of brackets that we can make 0. When that happens, what you should do is, since we could actually input any value of x here, inputting values of x such that the brackets became 0, that was more efficient because that eliminated some of the unknowns. But now, since we don't have any brackets that we can make 0, what we do in such cases is we try small positive values. First of all, 0, but then small positive values of x, and then we solve the equations that we get as a result of that. For example, in this case, we input x equals minus 1 initially. Now, since there's no other bracket that we can make 0, what we do is we say, let's input x equal to 0 next. Now, when we input x equals 0, what happens in this case is this is b times x here, right? So when x is 0, when x becomes 0, this gets eliminated. You already know the value for a, that's minus 1. You can use that here. And that will give you the value for c, which turns out to be 1, right? Because b gets eliminated in this case when we input x equal to 0. And then finally, put another value of x. You can put x equals 1. Small positive integers, they're going to be easy to calculate and save you from careless errors. X equals 1, that's the next value that you can input. Now you already know the value for a, you already know the value for c, and you'll get the value of b from that, okay? And these are the partial fractions that we get eventually, minus 1 over 1 plus x plus 2x plus 1 divided by that, okay? Now, what if you had something like this? So sometimes you can get fractions that have x square in the denominator like this. Now, how do you treat this? How do you treat x square? Is this a repeated linear factor? You could think of it like this. You could say this is x and then whole squared. So it's a repeated linear factor. That's one way of thinking about this. Another way of thinking about this could be that you say this is a quadratic factor, right? With x squared. And in that case, you would say that's ax plus b divided by x squared. You could also do that. However, although they accept this a lot of times in the marking scheme, it's better to treat this as a repeated linear because that further splits the fractions, and ideally that's what we want. If we treat it as repeated linear like this, then the form that we would get in that case would be a over x plus b over x squared plus c over 10 minus x. Okay, and that's a better way of writing this rather than treating this as a quadratic factor. Now, if we do it this way, what happens in the next step now? We multiply this denominator on the right side and we get ax into 10 minus x plus b into this plus cx squared. Now we have to think about what brackets we can make 0. We can make this bracket 0, that's x equals 10. That gives us the value for c. And now we have run out of brackets. What do we do then? We can input x equal to 0 then. X equal to 0, when we do that, c gets eliminated in this case. And we already have the value for, in fact, we have the value for c, that doesn't matter. We input x equal to 0, and that gives us the value for b here. Then we input x equals 1, because now we've run out of brackets. We use any small positive integers, x equals 1, and that gives us the third solution. Okay, a, b, and c. And that's the factorized form that you end up getting from this. Okay, let's have a look at this example. Now, what about this? This is 7x squared minus 3x plus 2 over x into x squared plus 1. You've got a linear factor, non-repeated linear, a over x is the form that we have for that. X squared plus 1, that's a quadratic factor. For that, we have bx plus c in the numerator. Now, in this case, you see what's happening. When we multiply the denominator on the right side, this is what we end up getting on the right side. Now, can we make this bracket 0 somehow? We can't. X squared plus 1 equal to 0. That does not give us any value for x. So what do we do then? We input x equal to 0 first of all, because when this becomes 0, bx plus c, that will get eliminated. So we could start from that, input x equals 0, and that gives us the value for a. Now, in this case, when we input small positive values of x, we can input x equals 1, x equals 2. This is one case in which you end up having to solve simultaneous equations. Otherwise, this method is very efficient in 95%, 99% of the cases. This is one case in which sometimes you end up having to solve simultaneous equations because some variable does not get eliminated. So in this case, when you input x equals 1, you get b plus c equals 2. X equals 2, that gives you this. And you have to solve these simultaneous equations. You can do that, solve them simultaneously, find the values of b and c. Now, only in this particular case, there's an alternative that you could use. That alternative is a general method that also works in most cases. But in most cases, this is more efficient than what we're doing here. However, once it turns out that you end up having to solve simultaneous equations in some rare case like this, what you would do would be, you would say, okay, let's find whatever constants we can easily use in this method, first of all. So x equals 0, that gives you the value for a directly. So that's pretty straightforward to figure out. Now, once you've done that, once you have found the value for a like this, that turns out to be 2, then you could use comparison method after this. You could say, okay, this is the expression that we've got. Let's simplify both sides. Simplify, the left-hand side is already simplified. The right-hand side, we could simplify this, and then see what is the coefficient of x squared, what is the coefficient of x, what's the constant, and then you do comparison. In this case, this would be more efficient. Compare the coefficients of x squared, that gives you the value for b. Compare the coefficients of x, that gives you the value for c, and that becomes much quicker as compared to solving that simultaneous equation. So this is what I would recommend. This is the general method that you use in every single case, inputting values of x like this. In some rare case, it doesn't happen very often, very rare, in which you end up having to solve simultaneous equations because you cannot eliminate the variables. In that case, you stop at this point, and from this point onward, you do comparison instead, and that will make it a bit more efficient like this. Okay. Otherwise, in general, this is not as efficient as the other method. You will have to solve simultaneous equations and in most cases and while you're doing comparison. So it's better to use that method where we input values of x like this. All right. Okay. Now, what about improper fractions? You can have improper fractions as well. In numbers, improper fractions used to look like this. If the numerator was smaller, we used to call them proper fraction. If the numerator was bigger, we used to call them improper fractions. What about polynomials? In polynomials, first of all, you need to know what the degree of a polynomial is. Degree of a polynomial is the highest power of a polynomial in simplified form. For example, this polynomial, its highest power is 3. We say the degree is 3. This polynomial, what's the highest power? X into 2x squared. The highest power would be what we get after multiplication of x and 2x squared. In simplified form, the highest power is 3. We say that's the degree. Similarly, here as well, what's the highest power in simplified form? If we were to expand this, we would have an x squared from this. We'll have an x here. We multiply them, we get x cubed. So the degree of this polynomial is 3, right? That's how we find the degree. Highest power in simplified form. Now, a proper fraction is one in which the degree of the numerator is less than the degree of the denominator. All the examples that I showed you earlier, all of them were proper fractions because in them, the degree of the numerator was less than the degree of the denominator. Now, sometimes you can have improper fractions as well. What are improper fractions? Improper fractions are fractions in which the degree of the numerator is greater than or equal to the degree of the denominator. Now, in partial fractions, you will only have to deal with one of these cases. In partial fractions, you only have to deal with this case when the degree of the numerator and the denominator, that's equal, okay? You would not have to deal with the greater than case. That will come later on in integration in some questions, but not in partial fractions directly. In partial fractions, it will always be equal, okay? For improper fractions, the degree would be equal. For example, if you have a fraction like this, x plus 3 over 2x squared plus 1 into x plus 5, the first one, the degree of the numerator is 1. For the denominator is 3. We say it's a proper fraction. For the second case, the degree of the numerator is 3. For the denominator, it's also 3. They're equal to each other. So we say it's an improper fraction. Okay. Now, for improper fractions, we would not have the same forms as before. It will be slightly different. What happens is, we have another constant in improper fractions. So you have non-repeated linear factors, we would still get those 3 fractions with those denominators separately, 2x minus 1, x plus 3, x minus 4. But we would have an additional constant with them like this. One additional constant. We'll have an a, or you can put that in the beginning or at the end, it doesn't matter. Similarly, for quadratic factors, for repeated linear factor as well, the other terms remain the same. X plus 5 is coming once, x minus 3 whole squared. However, we have an additional constant that is added here. And similarly, for quadratic factor as well, the standard form that was there before for proper fractions, that remains the same. However, you just have one additional constant added to it. So the improper fractions in the standard forms, we have an additional constant like this. Okay. Okay, there's Azan going on here. I'll explain what to do with this additional constant after that. 1 minute break and then resume after that. Okay, so in improper fractions, what we have is an additional constant in the beginning like this, or at the end, it doesn't matter. We could put that anywhere. Now, how do you find the value of this constant? Where does it come from? Basically, remember in numbers, when we have improper fractions, we could write them like this. quotient plus remainder over divisor, right? We could break them into quotient plus remainder over divisor. So that's what's happening here as well. When we have an improper fraction, what we can actually do is we can do long division, and then break it into two parts like this: quotient plus remainder over divisor. Okay. And then for this, you find the partial fractions the normal way, because then this becomes a proper fraction. And we have a constant on the side, since we will only have the case in partial fraction when the degree of the numerator and the denominator is the same. The quotient will always just be a constant. So since it's always going to be a constant, what we can do is, instead of doing that long division process, this is actually the background for this is where it comes from. But instead of doing that long division process, since we know there's just going to be a constant that's going to be added, we can add that in the standard form, and we can say whenever we have an improper fraction, we will just have an additional constant here like this. And how would we find the value of a value of this additional constant? Can be found directly. How? You would just divide the highest power term of the numerator with the highest power term of the denominator in simplified form. So x cubed, that's the highest power term of the numerator. In the denominator, what's the highest power term that you have? 2x into x into x, that's 2x cubed. You divide x cubed by 2x cubed, you get 1 over 2. So you know the value of a is going to be 1 over 2. You can just input that here, and the rest of the process remains the same. You multiply this denominator on the right side with the whole thing, including this constant. It also will be multiplied here. And then you input some values of x, as we used to do before, that can make some bracket 0, and solve that further. Similarly, in the next example here, how can we find the value for a? The coefficient of x cubed in the numerator is 2x cubed, the highest power term in the denominator. That would be x into x squared from here. That's x squared, x cubed, sorry. 2x cubed over x cubed, the value of that constant turns out to be 2. So we don't even have to do long division process. We can find this quotient directly by just doing this division. Similarly here, this is x power 4 in the numerator, 2x raised to power 4 in the denominator. The value of a turns out to be 1 over 2. In this case, it's 2x cubed in the numerator, 3x cubed in the denominator, a equals 2 over 3. So how do you find the value of a? It's just the highest power term of the numerator divided by the highest power term of the denominator. Now, these are the forms that we brought for improper fractions. The same as before, we just have an additional constant added to those earlier forms that we had for proper fractions. Now, how would we actually do this? This is an example of that. This is an improper fraction. This is the first thing that you always have to do now. Whatever fraction you have, the first thing you do is you figure out whether it's a proper fraction or an improper fraction. In this case, the degree of the numerator is 2. For the denominator, it's also 2. Same degree, that means it's improper. So in the form that you have for this, a lot of times people end up forgetting this. You will have this additional constant here. Do not forget that. It's an improper fraction, you have an additional constant like this. And the value of that additional constant, you can find that directly as we discussed. A turns out to be 2 from this. That's 4x squared divided by x into 2x. That's 2x squared. And that gives you 2. Once you have that value of a, you can input that here. Multiply the denominator on the right side. Simplify and then just input some values of x that can make any bracket 0. In this case, I input x equals -1. That gives me the value for b. X equals 3 over 2. That gives me the other value, and that's it. We've got the partial fractions. Remember, when you multiply this denominator on the right side, it will also get multiplied by 2. Do not forget that. 2 will also be multiplying with that. And you get the partial fraction form for that. That looks like this. Okay. This is another example. Sometimes they give you the form like this. Again, it's an improper fraction, right? Because the degree of the numerator is 3. Degree of the denominator is also 3. They have this additional constant here. We know how to find the value of that constant. That's x cubed over x cubed. In this case, a turns out to be 1. And then we follow that same process that we did before to find the values of b, c, and d. You can have a look at this here. One last example from a recent paper. So they can have these constants here in partial fractions sometimes as well. So this is 36a squared divided by 2a plus x, 2a minus x, 5a minus 3x. Now, 5a minus 2x, they've tried to make it a bit more complicated by introducing the letters there, the letter a there. How would you do this? These are linear factors. The powers of x are all 1. So these are repeat and non-repeated linear factors. You'll have a form like this for this. And then you do it the normal way, not getting scared by that letter A. Multiply the denominator on the left side on the right side. Then you have to make these brackets 0. So 2a minus x, how can this be equal to 0? X should be equal to 2a. You input x equal to 2a, and that gives you the value for b. And then 5a minus 2x, how can that be 0? You input x equals 5 over 2a. That gives you another value. So I've done that here, the value for c. Then make another bracket 0. This bracket 0, that's x equals minus 2a. You input x equals minus 2a, and you get the value for a from that as well. And then you have the partial fractions from that. Make sense? Sometimes you can have something like this as well, in terms of a like this, right? The process remains exactly the same as before. You just have to be a bit more careful with the algebra because the probability of making careless errors increases here a bit. Okay, all right, let's move on. Actually, this is integration. I copied that by mistake. I will just remove that from here. And that's it. That's all that you need to know about partial fractions. We'll talk about the binomial part when we do binomial next. But as far as partial fractions is concerned, this is all that you need to know about integration, differentiation. That can make you do more errors there, and that's not going to help. Okay, so this is the next topic that we're starting. Binomial expansion. Now, first of all, we need to know what factorial function is. Now, at this point, all of you have done S1 already, so you know what factorial is, right? So that's what you need to know about, because that's used in the formula. 1 plus x raised to power n, this is the formula that's given in the formula sheet, is equal to 1 plus nx into n minus 1 over 2 factorial into x squared, and so on. It's given up to the x cubed term here in the formula sheet, right? So this is what I've taken from the formula sheet. This is what you do to expand expressions that look like this: 1 plus x whole raised to power n. Now, there's some conditions that this formula has, and they note them down here. N is supposed to be a rational number. Now, what's a rational number? Anything that can be written as a fraction that includes integers. Now, generally, the questions that you would get, they would have either a fraction as the power. It could be positive or negative, or it would have a negative integer as the power. If it's a positive integer, for that you could use the first formula as well, the P1 binomial formula. So that will normally not be tested here. In this case, I'll either have a negative integer power or a positive or negative fraction. Now, in order to use this formula, the expression that you have here, it needs to have 1 as the first term, and then the second term could be anything, but the first term has to be the constant 1. It can't be x. Anything in terms of x, it has to be 1, okay, and nothing else. If you want to use the formula like this. Now, how does this formula work for expansion? You'll just input values compared with the standard form. 1 plus x whole raised to power minus 3. Compared with the formula, you've got 1 plus x inside. The formula also has the same thing. The power is minus 3. You put n equal to minus 3 in the formula here, and then just simplify everything. You get this expansion. That's fairly straightforward. Now, you generally don't have to go beyond this. They will only ask you to expand up to this. But in case you do have to expand further, it will be a maximum of 1 more term. Looking at the pattern, you can see what the next term should look like. It should be n into n minus 1 into n minus 2 into n minus 3 divided by 4 factorial into x raised to power 4, right? That's the maximum that you might have to go in some question, but normally it's going to be only up to these terms. And they will specify up to what point you have to expand. Let's take this example, 1 minus x over 3. Now, in this case, inside the bracket, in place of x, we have minus x over 3. So what we're going to do now is, in place of x in the formula, we would write minus x over 3, right? The formula has plus, this has minus. So that means in place of x, you have to put minus x over 3. Then just input values in the formula. In place of n, you put minus 2. In place of x, wherever you have x in the formula, you have to replace that with minus x over 3. Now, when you do that, especially for negative numbers, make sure that you put them inside brackets like this. If you don't use brackets, you will end up making errors because of that. Now, how do you actually do this calculation? Because a lot of times, a lot of errors happen when you do these calculations. Once you have input values in the formula like this, you will show the step. It's necessary to show the step. Then you can write down the answers like this. You will just evaluate the powers of x yourself. This is x power 1, this is x power 2, this is x power 3. The rest of it, you will just put that whole thing on your calculator directly. For example, let me just show that to you for the last term here. You would just put that whole thing on your calculator exactly in the same format. You would say that it looks like this. Okay, I have that now. You'll input this whole thing on your calculator. Minus 2 into minus 2 minus 1 into minus 2 minus 2. There's some calculation that you can actually do it in your head as well. Minus 2 minus 2 is minus 4, minus 2 minus 5 is minus 3. So you have that here. Divided by 3 factorial, which is 6. You could write 6 if you remember that, or you could just write 3 factorial. Now, what do we do with x? In place of x, you write 1. Okay, in place of x, you write 1 in your calculator. So it becomes minus 1 divided by 3 and then whole cube. Just put this whole thing on your calculator like this. And that will give you this number 4 over 27. And now you can just write the power of x alongside that. That's x cubed, and that's it. That's your final result. So you can put this whole thing on your calculator like this, making sure that you are copying this correctly on your calculator and put this exactly in the same format using the fraction button on your calculator. And that will save you from errors. That's how this would work. Now, the power could be fraction as well, right? The power could be fraction as well. For example, you could have minus 1 over 3 here like this. What about this now? In place of x, you would have to input minus x squared over 4. And in place of n, you would put minus 1 over 3. And then just simplify this again. In place of x on your calculator, you would put 1. And then just put this on your calculator. That will give you the coefficients. You would write x squared with this yourself. This is x squared whole squared. That's x power 4. You can add x power 4 here. And that gives you the expansion. This is so we input this on our, so there's a question that shouldn't this be negative because there's a negative there. In our calculator, when we input this, we just replaced x with 1. We put minus inside the bracket there. We put minus 1 over 3 there inside the bracket, right? So this minus is already being used in that calculation, and that's giving us a positive number because we have this negative, 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 4 negative, that becomes a positive. So we just think of x cube ourselves, that's a 6 cube there. Okay, that's the result that we get. Okay, let's take another example. Now, the complicated part here is sometimes when you do not have 1 as the first term. For example, if you have 2 as the first term here, how would you expand this? Now, the formula requires that the first term is 1. So first of all, what you have to do is you have to make the first term 1. How would you do that? You can take 2 common outside. Now, when you take 2 common outside, it becomes something like this. 2 into 1 minus x squared over 2 whole raised to power minus 3. The power is on the whole thing. So when we take 2 common outside, the power is still outside there. So now we can say, using this indices rule, that a into b whole raised to power m, that's the same thing as saying a raised to power m into b raised to power m. So that would become 2 raised to power minus 3 into this whole expression power minus 3, right? You do not necessarily have to write down this step. You can just directly write this as well. Make sure whatever you're taking common outside, that should have that number as the power as well. So now outside you have 1 over 2 cubed. This expression now is the standard form that you want for the formula 1 plus x whole raised to power n. You can input values in the formula now, simplify that, and then at the end you multiply 1 over 8 with that, and you get that expansion. Okay. Now, you could have something like this, 2x minus 3 whole raised to power negative 2. Now, in this case, you see what's happening? The first term is not even a constant. It's something in terms of x. How would you expand this? First of all, you'd have to make the constant the first term. So you can rearrange this, right? This is 2x minus 3. I can say, let's write minus 3 first and plus 2x second, right? I'm just rearranging this. So if you had, for example, 7 minus 4, that's the same thing as minus 4 plus 7, right? So I'm just writing the constant first and the x term second. And now we want to make this constant 1. What do we do for that? We can take minus 3 common outside. When we take minus 3 common outside, remember that is also going to have the power minus 2. It's a negative number. Always make sure write this inside the brackets like this. Otherwise, you do sign errors. Always write these numbers inside brackets. So this has power minus 2. And then inside, we're just left with 1 minus 2 over 3 times x power minus 2. Now, how do we get minus 2 over 3 from this? Remember when we take something common outside, for example, if we had 4x plus 8 and we take 4 common outside, what actually happens is we are saying we're writing 4 outside, so divide 4x by 4 and that gives you x, divide 8 by 4 and that gives you 2. So we have 4 into x plus 2 here as well. When we take minus 3 common outside, what that means is divide minus 3 by minus 3 and that gives you 1. And for the second term as well, divide 2x by minus 3 and that becomes minus 2x over 3. That's what we end up getting inside the bracket. And now this is something that we can use the formula for, input values in the formula, and then simplify that. At the end, you multiply the 1 over 9 that you got outside inside the bracket, and that will simplify things. A lot of careless errors happen here. Make sure that you're careful about the negative signs. If there's a power on top of them, always write them inside brackets like this. Okay, so that's how you would expand something like this. Now, there's a question that they ask after you've done a binomial expansion. So this is 1 plus 3x whole raised to power minus 1 over 3. They want you to expand this, first of all, up to and including the term in x squared. Let's say you've done that. But then they're saying, state the set of values of x for which this expansion is valid, Now, what does that mean? Now, if you look at the formula, I did not talk about this condition before, but now let's talk about that. There's another condition at the end that's given. The modulus of x has to be less than 1. This formula is only valid when the modulus of x is less than 1. Now, what does that mean? Modulus of x less than 1? That's the same thing as saying x is between minus 1 and 1. Right? You can write it both ways. You can say modulus of x is less than 1 or x is between minus 1 and 1. They are equivalent. What that means is, when you're using this formula, whatever you have in place of x, this thing has to be between minus 1 and 1. Only then the formula would work. Otherwise, this formula would not work. So when you're doing this expansion, 1 plus 3x whole raised to power minus 1 over 3, what do we have in place of 3x? What do we have in place of x here? We've got 3x. So 3x should be between minus 1 and 1. So you can do it both ways, using modulus or without the modulus. You could say either modulus of 3x is less than 1, and that gives you modulus of x less than 1 over 3. If you get confused with the modulus function, this is an easier way of doing this. You say 3x has to be between minus 1 and 1. Now, what about x then? We divide the whole inequality by 3, and that gives us x between minus 1 over 3 and plus 1 over 3. This is the set of values of x for which this expansion would be valid. Okay, so whatever is in this place, you put that between minus 1 and 1. Let's have a look at some more examples of that. So this is actually the reasoning why that is important, because when x is small, since you see this sequence, it's going up to infinity. It's a never-ending sequence. The reason why we can ignore, so this is actually important because we will have some questions that refer to this. So let's actually quickly discuss this. Why is that condition important? Because this is an infinite sequence. The next term would be x power 4, x power 5, x power 6, and so on, all the way up to infinity. Why are we not writing all of those terms? How can we just expand the first few terms and say, okay, this is the expansion of this, when there are infinitely many terms that we're not writing, x power 4, 5, 6, 7, all the way up to infinity? Why can we ignore them? This condition that we've got, this is what allows us to ignore them, because when x is a value that is between minus 1 and 1, for example, if it's 0.5, let's say, if we take powers of a number that's less than 1, what happens is the powers become, when you evaluate those powers, those numbers get smaller and smaller. So higher powers the bigger powers, they would actually be smaller numbers. For example, x power 10 in this case, that's very small. So as you go further in the sequence, the values keep getting smaller. The values keep getting smaller. That is why we just expand the first few terms in that, and we say that that's a good enough expansion for this expression, because the rest of the terms, they're kind of negligible. That's why this condition is there. Now, let's have a look at some more examples. I'll come back to that. Expand cube root of 1 minus 6x. Okay, now how do we do this? Cube root of 1 minus 6x. We first of all write this in power form, so it becomes 1 minus 6x whole raised to power 1 over 3, and then we expand it like we normally do. We input values in the formula, and then we just simplify that. Now, you can get questions like P1 binomial in this case sometimes as well. For example, they have a product like this, and they're asking for the coefficient of x cubed in this expansion. How would you find that? If we want x cubed, which terms do we want from this expansion? 3 will have to be multiplied by x cubed. To get x cubed, x will have to be multiplied by x squared to get x cubed. So from this expansion, we need x squared and x cubed. So we have to expand that up to x cubed. We expand that expression up to the term in x cubed here like this. That gives us this. And then we evaluate that product 3 minus x times that expression, which are the two terms that we wanted from that x squared term and x cubed term. So we just focus on those two terms. We ignore the rest of them. We say 3 minus x into this minus x squared plus 5 over 3x cubed. We just take those two terms. And from that, we can get the coefficient of x cubed. That turns out to be 6. Okay, so we used to do problems like these in P1 binomial. You end up getting something like this in P3 sometimes as well. Okay, then this is another example that you've got 1 plus ax whole raised to power minus 2. A is a positive constant, and they're saying the coefficients of x and x cube are equal in this. Now, how do you find the value of a from this? You just apply the formula on this expression, apply the formula, simplify everything, and whatever is the coefficient of x that you get, and whatever is the coefficient of x cube that you get, you equate both of them. So in this case, when you do the expansion, when you apply the formula on this, you get minus 2a as the coefficient of x, you get minus 4a cube as the coefficient of x cube. You equate both of them, and that gives you one possible value of a, that is 0. But that's not possible because the question said that a is supposed to be a positive constant. The other possible value of a that we get is 1 over under root 2. We ignore the negative here as well because a is supposed to be a positive constant. And the value of a that we end up getting from this is 1 over square root of 2. And that is our final answer. Okay. And then they say expand this up to x squared. You can do that when you input that value of a. So you've done this expansion here already. You can just input the value of a in this and then simplify that, and that gives you that expansion. So sometimes you end up getting questions like this as well, similar to P1 binomial, where they're looking for specific terms in the expansion. But that's not that difficult. You just expand it like you normally do, and then just use those specific terms that they're talking about. Now, let's have a look at this. It says, show that for small values of x squared, this expression is approximately equal to kx raised to power 4. Now, how do we understand the statement? The working is exactly the same as what we have been doing until now. However, they are saying for small values of x squared. Now, what does that mean? As we discussed earlier, when x is very small, in this case, they're saying x squared is very small. What happens is when you take higher powers of that, for example, in this expansion, you would have a constant, first of all, 1, and then you would have n into x. In place of x, you've got x squared, right? So the terms that you would get from this, they would be 1, x squared, x power 4, x power 6, x power 8, and so on in this expansion. If x squared is small, they are saying we could ignore the bigger powers. So you just ignore the bigger powers, only expand this up to x raised to power 4. That's all that it means. You'll do the expansion like you normally do. You've got two different expressions to evaluate, to expand here. One is this, 1 minus 2x squared whole raised to power minus 2. We do this expansion. In place of x, we've got minus 2x squared. We do the expansion up to x raised to power 4. Why? Because they're saying x squared is small, so we can ignore the bigger powers. Right? We can ignore the bigger powers after x raised to power 4. So we expand it up to x raised to power 4, and this is what we get. And then we expand this other bracket, expand this again using the binomial expansion formula, and that gives you this. Then find their difference. So in this case, what I've done is I've used the minus sign along with this expression here. So when I simplify this, I can just add those two results now, this and this, and that gives me the final result. You see what's happening in the final result? The constants get cancelled, the x squared terms can get cancelled, and we're just left with 16x raised to power 4, and that's what they wanted us to show, that this thing can be written as kx raised to power 4. We are getting 16x raised to power 4. What's the value of k that we get from this? The value of k is 16, and that's what we wanted to find out. So when they say x is small or x squared is small, what do you understand from that? What do you understand from that? That the higher powers can be neglected. They are negligible. They can be ignored. That's what we understand from that. Okay. Why do we not have x and x cube in this? Because in place of x, you see the value that we're inputting in the formula. In place of x, we've got minus 2x squared here. In place of x, we've got 6x squared. So we have x squared here. X squared power 1 is x squared. X squared power 2 is x raised to power 4. X squared power 3 is x power 6. So we won't be getting the odd powers in this case because of that, right? So this is what we get. All right, this is another example. Now, sometimes you can have that expression in the denominator like this, square root of 4 minus 3x in the denominator. What do we do with this? You're not going to expand it in the denominator. You will first have to bring it to the numerator and then expand it, because it says ascending powers of x. Ascending powers cannot be in the denominator. They have to be in the numerator. So first of all, you bring that expression to the numerator. Its square root, you can write that as power 1 over 2, and then you take that to the numerator, and that will make it power minus 1 over 2. And now the first term is not 1. You have to make it 1. You take 4 common outside, and that gives you 4 power minus 1 over 2 here. Inside, you have the standard form now. You apply the formula on that, and then at the end, you simplify that, and you get the result. In this case, now let's take this example. If they had asked you for finding the values of x for which this expansion is valid, how would you do that? What would you put between minus 1 and 1? Do we put 3x between minus 1 and 1? Or this between minus and 1? After we have converted it to the standard form, this thing that we're having, this should be put between minus 1 and 1, right? Because that's what we're applying the formula on. This is the expression on which we're applying the formula. So if they asked you for what values of x is this expansion valid, you would say this is 1 minus 3x over 4 whole raised to power minus 1 over 2. In this position, we are getting minus 3x over 4. In this case, we can actually ignore the sign because it would not matter. I'll tell you why. You just say 3x over 4 should be between minus 1 and 1. And that gives you, when you multiply by 4 on both sides, that gives you minus 4 and 4. Divide by 3, and that gives you x between minus 4 over 3 and plus 4 over 3. This is the set of values of x for which this expansion is valid. Now, in this case, if you have a negative sign here, for finding this interval, you could actually ignore this. It would not make any difference. That will simplify things for you. The reason is, if you had minus 3x over 4 between minus 1 and 1, if we multiply this inequality by minus 1, we can do that, right? We're going to multiply with negative 1. Now, this would become 1. Multiplication with negative sign would change the inequality sign as well, and that will become 1 greater than 3x over 4 greater than minus 1. And that's actually the same thing as this, right? It doesn't make any difference. Even if you have a negative sign there, the end result is going to remain the same. So when you're finding the set of values of x like this, you would ignore the negative. That will simplify things for you. Just put this thing between -1 and 1 and see whatever values of x, whatever set of values of x you get from that, that's going to be the solution. Okay? That's going to be the set of values of x that satisfies that condition. Now, you will get this in partial fractions as well now. In the first part of a question, they will ask you to find partial fractions of something. And then in the second part, they will ask you to expand that in ascending or descending powers of x. Now, let's say they wanted you to do that in this case. In the first part, you find the partial fractions, and this is what they turn out to be. And then you have to obtain the expansion of this in ascending powers of x. Now, how would you do that? We already have the partial fractions here. These are the partial fractions that we've got. I've skipped the first part here. We already have the partial fractions from the first part. This is what they look like. Now what we do is we have to expand it in ascending powers of x. How would we do that? We first of all bring this denominator to the numerator. Bring all of these denominators to the numerator. What does that become? For the first term, we get 1 into x plus 1 power minus 1. For the second term, we have 2 into x plus 1 power minus 2. Then minus 3 into 3x plus 2 whole raised to power minus 1. Now, this is how I would recommend that you approach it. Simplify these so that all of them are first converted to the standard form. Okay. What's the standard form that we need for the formula? 1 plus x whole raised to power n. First of all, convert all of these to that form. What about the first term? This is x plus 1. You can just rearrange this and write that as 1 plus x, and that's it. This is the standard form for the first term, and that's okay. What about this? In this case as well, you can just rearrange them. X plus 1, that can be written as 1 plus x, and that becomes the standard form as well. For the last one, you first have to rearrange that and write the constant as the first term, so it becomes 2 plus 3x. And then you have to make this constant 1. How would you do that? You take 2 common outside. When you take 2 common outside, do not forget that 2 will also have the power minus 1. So you have 2 power minus 1 into 1 plus 3x over 2 whole power minus 1. And now all of these are in the standard form. Okay. Now, since you would have an A4 sized paper in the exam, you would not be able to expand all of these in the same line, right? Unless you write extremely small, which is not recommended. That will make you do careless errors. So what you should do at this point is, once you have standardized them, as in you've found the standard forms for all of them, now you expand each one of them separately. So let's call this the first expression. Let's expand this separately, 1 plus x whole power minus 1. Apply the formula on that, simplify that, and you get the result. Then the second term, do not just pick this 1 plus x whole power minus 2. Pick up this whole expression. Otherwise, at the end, you would forget that there was a 2 multiplying there, and you will end up making mistakes. Pick up the whole thing from here. 2 into 1 plus x whole power minus 2. Okay, write that here. That's the second expansion that you have to do. Do this expansion, multiply 2, simplify this. This is what you end up getting for the second expansion. Similarly, the third expansion, again, pick up this whole thing from here, including the negative sign. Pick up the whole thing from here. What's that? That's minus 3 over 2, 2 power minus 1, that becomes 1 over 2x. That goes to the denominator, and you have minus 3 over 2 into 1 plus 3x over 2 power minus 1. You apply the expansion formula on this, and then multiply minus 3 over 2, and that simplifies to this. Okay. So whatever numbers we're multiplying there, including the negative signs, we have already simplified everything until this point. We've got these 3 expansions now. All we have to do now is add them up together. So we can write them like this, like terms on top of each other like this. This is the first expansion, second expansion, third expansion. Add them up together, and you would get the result. You can put these on your calculator one by one. Input this on your calculator, you'll get 3 over 2 from that. Input the coefficients here in your calculator, minus 1, minus 4, plus 9 over 4. And input the coefficients here on your calculator, 1, 6, and minus 27 over 8. And that will simplify things for you. And that's the final result that you end up getting from this. That's how you would do this expansion in cases where you have partial fractions and binomial. Now, this is very important. Sometimes, again, in recent papers, you would see that they would ask you to state now the values of x, the set of values of x for which this expansion is valid. Now, you are doing three different expansions here. You're applying binomial formula on three different expressions here, on this, and on this. You're applying binomial formula on these three expressions, right? Now, how do you write down the set of values of x from this? For which these expansions are valid. For each of them, it will be a different set of values of x. These are the three different expansions that we have done: 1 plus x power minus 1, 1 plus x power minus 2, and 1 plus 3x over 2 power minus 1. These are the expansions that we have done here. For each one of them, we can find the set of values of x for which the expansion is valid, right? In the first case, x should be between minus 1 and 1. In the second case, x should be between minus 1 and 1. In the third case, 3x over 2 should be between minus 1 and 1. Now that gives us that x should be between minus 2 over 3 and 2 over 3. Now we are getting from one expansion that x should be between minus 2 over 3 and plus 2 over 3, and from another expansion that x should be between minus 1 and plus 1. What's the final result that we get from this? Do we write this or this? We have to see what is common between them. Which values of x satisfy all conditions, which values of x, for which values of x are all of these expansions valid? So you've got minus 1 to 1 on this number line, minus 1 to 1. That's one set of values of x that you're getting. And you have minus 2 over 3 to plus 2 over 3. What's common between them? Common is the minus 2 over 3 and 2 over 3. That's the overlapping part. That is what you would write there. That's the overlapping part, right? Minus 2 over 3 to plus 2 over 3. So that's the final interval that you write there. It's supposed to be between minus 2 over 3 and plus 2 over 3. That's the final set of values that you write. You do not write this. You write this. Okay? Because that's where both of these conditions are overlapping. When x is between these two values, all of these expansions would be valid at the same time. Okay. All right. Just one last example, a couple of just one or two more examples, then we move on. We have this that we want to express in partial fractions. And the first part, we just do that. And then we have to find this in ascending powers of x. Now, how do we do that? We find the partial fraction in the first part that turns out to be this. And now, how do we do that expansion? Okay, now let me go through this again. So hopefully it's correct now, or there might be some careless error somewhere else, but it's okay. You get the idea from that. So in the first part, we find the partial fraction. In the first part, we find the partial fractions. Okay, and then we have to do the expansion here. So we take x plus 2 to the numerator. First of all, it becomes x plus 2 whole power minus 1. And we take this to the numerator, and that becomes x squared plus 1 whole power minus 1, right? And now we have to do these expansions. How do we do that? First of all, we convert them to standard form. We take 2 common outside from here, and that also has 2 power minus 1. We take this remains as it is. This is already the standard form, and then we expand these two separately. Again, pick up the complete expressions. Pick up the complete thing from here. 1 plus x over 2 whole power minus 1. That's your first expansion. Simplify that. This is what you end up getting from that. Similarly, do the other one. The whole thing, x minus 1 into 1 plus x squared whole raised to power minus 1. Do this expansion. You'll do this expansion first of all. You have to do it up to x cubed. You get x squared as the second term. The next term would have been x power 4. So we just stop here at x squared, simplify this, and we end up getting this. Now, before you add, it's a good idea to first write this in ascending powers. So it becomes minus 1 plus x squared minus x cubed. And then you just add these two up together, and that would give you the result. Okay, so that's the idea. That's how you can do these partial fractions and binomial problem. Just one last example. if you had this square root of 1 minus x over 1 plus x, how would you expand this? Up to x squared. You can write this in power form. First of all, you can say that's the same thing as saying power 1 over 2. And in the denominator, you have power 1 over 2 as well. Then you bring that to the numerator, it becomes power minus 1 over 2 here. And now you just expand both of them separately. This is what the expansions turn out to be. Simplify them and then simplify them further. Ignore the terms that have powers greater than x squared. And this is what the final answer turns out to be from this. Okay, so that's all that we need to know about binomial expansion. I hope that makes sense. Any quick questions before we move on? Okay, so that's actually a good one. So can you tell me the expression that you would have? Let me just ignore that. I'll just do this. Okay, yeah. All right, let's actually redo this. Okay, it's a bit complicated, but let me explain this again. Okay, so let's say we've got this 1 minus x squared over 2 whole raised to power minus 3. If we have 1 minus x squared over 2 whole raised to power minus 3, and we wanted to find the set of values of x for which this expansion is valid, how would we do that? First of all, we ignore the negative sign. As I mentioned earlier, that would not make any difference. We would say x squared over 2 is between minus 1 and plus 1. Okay. All right. Now, 2 goes to the other side. It goes to the other side as well. We multiply the whole inequality by 2. So that gives us minus 2 between x squared between minus 2 and plus 2. Okay. Now, this lower limit is actually kind of irrelevant, right? Because x squared can never be negative. So there's no lower limit as such, right? It could be... since negative is not even possible, we could just think of it as x squared between 0 and 2 as before, right? So we could say that since x squared cannot be negative, the only possible values of x squared that we get from that are from 0 to 2. It could be equal to 0, but not less than 0. But now x squared is between 0 and 2. We would have to solve it as two separate inequalities. We say x squared is either greater than or equal to 0, because taking square root directly would be a problem. And then x squared is less than 2. Now it's a quadratic inequality. How do you solve quadratic inequalities? In the first case, it's just 0 on the other side. That would not make any difference. So from this, you just get x greater than or equal to 0. That does not make any difference. It's either this or the other condition. What's that? X squared is less than 2. Now, how do you solve this inequality? You first treat this as an equation. You say x squared is equal to 2. Treat it as an equation, solve this equation. X equals plus minus square root of 2. You get these two critical values of x from this. Now, we have a quadratic function. It looks like this. We have found the two cutoff points, the two x-intercepts. One is minus under root 2, the other is plus under root 2. It's a less than sign here. That means this region here. So x has to be between minus under root 2 and plus under root 2 here. That is actually the condition that we get from this. X is supposed to be between minus under root 2 and plus under root 2 in this case. This is the set of values of x for which this expansion would be valid. Or the other condition is this. Now, that's kind of irrelevant because this is the other condition that we're having, as in the other limit that we have is this. This is what we would consider. The lower limit is, it's obvious that x squared has to be greater than or equal to 0. Actually, we don't consider that because it would not make any difference. I'm not sure how exactly to explain that. This condition is kind of redundant, right? X squared is always going to be greater than or equal to 0. So even if we don't have that condition, it doesn't matter. Okay, so the only condition that really matters is this condition that the maximum possible value of x squared that should not be that has to be less than 2, and from that we get this that x is between minus under root 2 and plus under root 2. Does that make sense? That is how you would actually approach this. Yeah, but confusing. Greater than equal to 0 falls in the other category. Actually, from the other one as well. This would have been if we were to solve it properly. If we were to solve this properly, we would have gotten x squared equal to 0, x equals 0. That's the cutoff point that we're getting. And now this is what the curve looks like. It just touches the x-axis here. Now this is always equal to 0. So this is actually for all real values. So there's no condition that we have from this, because x squared is always greater than equal to 0. X squared is always greater than equal to 0. So from this we just get all real values of x. No matter what this is, this would always be true. So the only condition that really matters is this. That's x is between minus under root 2 and plus under root 2.